Alright, I'm going to start this video as I always do with my Heathkit test equipment videos by looking at Chuck Penson's excellent book, Heathkit Test Equipment Products. I'm going to flip to the oscilloscopes chapter, and I'm not going to try to give a history of all the oscilloscopes that Heathkit ever made. I'm really focusing on the digital oscilloscopes. So regarding the digital oscilloscopes of Heathkit, I have to rule out the ones that were not designed by Heathkit or which were perhaps available but only as assembled units or produced by other companies and branded Heathkit, which I know there were some of, although I don't have much information on those. So as far as ones that were actually designed by Heathkit and were digital oscilloscopes, there's only two models. One is the IC-4802. It's a 50 megahertz DC computer oscilloscope. It's a dual trace scope with no controls on the front. It only works by using a connected computer via RS-232 and software that Heathkit provided in DOS, which allowed you to operate the scope from the computer screen. So that's why it's just a box with only a pair of BNC connectors for the two channels. This came out in 1986 and was discontinued after 1990. Now, Chuck's book here says that this is functionally the same scope, essentially the same scope as the IC-4850, but that's not quite true. I think it had the same case and the same main circuit board, but with different software for the microprocessor, and certainly without a front panel, is quite obvious. Whereas the IC-4850 has the same specifications, except that it was kept around for an extra year through 1991, and it had a full front panel for the left, or the channel 1, channel 2, and the horizontal and triggering. Now, I actually owned one of these. I built it from a kit, and getting rid of it was one of the sorriest things I ever did. There was a period of time when I just thought it was unused junk in my lab that I wasn't using anymore, and I got rid of it, sold it on eBay, and ever since wished that I'd kept it. It was actually worked very well. It was a good little scope, albeit not a very fast one. And its resolution was not that great. I don't even know what it was. It might have only quantized to 8 bits or something. So not great resolution, but still usable. And I used that for a number of years, starting around '86 when I was doing a lot of contract engineering, and especially writing technical manuals for products made by companies that were owned by friends of mine. They found out that I wrote technically pretty well and wanted me to write their manuals or rewrite their manuals. And some of that included going to their facilities, hooking my IC-4850 up to their equipment and capturing waveforms, and then exporting those to be included in the manuals, you know, for setup calibration, that type of thing. So again, if you took the IC-4802 and replaced the front panel with this one, which also had a circuit board behind it for all of the LEDs. There's a great many LEDs on here, and the push buttons. And there's also 2 additional outputs, which the IC-4802 did not have. This could also be used to drive via these outputs here. You could use this with a single trace scope and then drive its the outputs from here into the inputs of that scope and have it show whatever waveforms this had captured using its normal 2 inputs. So it acted like a means to convert a single trace scope and or a slower oscilloscope into effectively a display device for the higher speed dual trace scope that this was. I've never actually seen one of these 4802s, but from all the descriptions I've seen, it did not have any outputs to drive an analog scope. So I think those are two areas that are the primary differentiators between this and the other model. Okay, here's the artifact. Just received from eBay. Looks pretty clean. I always loved the way this thing looked. It's just a really nice layout, nice color scheme, everything. This is done during that period of time when Heathkit was kind of leaving out parts of the model numbers on some of their test equipment. This should be an ID-4850 and they just list 4850. But yeah, so we've got all the buttons seem to be, nothing is stuck or spongy. You've got your two Y inputs here, your normal scope inputs. And then there's a trigger output and a vertical output to drive an analog oscilloscope. And then around the back, I won't show it yet, but there's just the power switch and the RS-232 jack, and that's it. So, just again as a quick overview, this is sort of a dual duty piece of equipment. If you have a analog oscilloscope, maybe it's only single trace and you want dual trace, you can use this as a way to convert that into a dual trace scope. Or if you have even a dual trace scope but it's slow and you want to measure higher frequency things up to 50 megahertz, which is the limit of this piece of equipment, then you could use this just to speed up your regular analog scope, again with two channels, even if the scope only has one. And then you can use it as a digital oscilloscope. The fact that it says memory on here isn't all that useful, but by connecting this to a computer you can essentially have a digital oscilloscope, even if you don't have any other oscilloscope, just using the screen of the computer to look at your waveforms. And you can take control of the front panel from the computer, or you can still use the ones on here, I believe. I think that you can make selections from either. I don't remember for sure, and I don't have the manual yet for this. But certainly you can use the buttons to control it if you're not connected to a computer. So you've got your channel 1 input here, just like channel 2, then your time base, and then your triggering functionality. So you've got your volts per division from 5 millivolts up to 5 volts, and by changing or pushing the up and down buttons for sensitivity, you can illuminate one of those LEDs. And then you can, if you want to center the vertical position, you just push both of these together, or otherwise you can raise and lower it using those. And then you can cycle through AC, DC, or ground for the input coupling. Same thing for the second channel. Time base is the same way. You've got 1 through 500, and that can be nanoseconds, microseconds, milliseconds, or seconds. So you can cycle through all of those with these two buttons. And this is a save button. And then over here you can select your trigger level, plus 0 or minus, the slope, plus or minus slope, your auto, normal, or single mode, cycle through those, a manual reset, and a ready light for the trigger, and then you can select whether you want vertical channel Y1 or Y2 as your source for the triggering. So very conventional oscilloscope inputs there. Alright, I've got the trigger and vertical output cables connected over to my Tektronix scope, and it looks like it's basically functioning. It's trying to draw two different waveforms on the screen, and it's saying error, no trigger. It's spelling that out in text. So I need to get this thing some signal to work with. Alright, that's working. I'm giving it a ramp wave on one signal and a sine wave on the other. And I'm getting those two signals here on the screen. It's triggering. The scope here is picking up the signals that this scope is sending out. Right now I've got it in single trigger mode. If I go to auto, I'd have to reread the instructions, but it seems like it goes away momentarily with that. If I put this in single, then it seems to be more stable on here. Now the two waveforms look pretty smooth to my eye, but they are of course being multiplexed, so the camera makes them look kind of jerky. Let's see here. I'm going to change the frequency on the sine wave to 2 kilohertz. And that did not change. I probably need to do another. Oh yeah, it's just holding the last waveform it triggered at. So I'm going to push the reset manual button, see if that gets a do. Yep, that did it. It took a new sample. So basically it's not continuously sampling at this point. It's doing one trigger because I basically told it to do one waveform or one scan and then stop. I'm going to go back to auto. It seems like it ought to work at auto a little better. I just changed which source it's triggering on. Alright, so let's just do another quick overview of this thing. There are two front panel boards. The front one appears to just have the LEDs and the push button switches soldered to it. And then through 1, 2, 3, 4 headers, it connects through to the second board, which has the digital logic on it for scanning the buttons and probably multiplexing the LEDs. Maybe they're energized all the time, the ones that are supposed to be on. I'm not sure of that yet. There's no analog stuff going on with this. The inputs come directly through these short shielded cables and plug into the main board. And however, the let's see. Yes, the output signals are apparently generated from this front board. So that yellow wire is coming from the trigger, and it's going up to the top of the board there, and the orange wire is the one for the analog output, and that's coming from way over here. So that makes sense, because even though I don't have a IC-4802, which is again the similar scope to this but without the provision for operating it autonomously, the 4802 needs to be connected to a scope or to a computer running a scope program in order to function. And it does not have the ability, that was a question I had, does it also have the ability to generate the signals to go into a traditional analog scope? I thought maybe it had the connectors around the back for that, but it does not. And I thought, well, then maybe all the circuitry that would generate those signals would be on the main board, and they just wouldn't populate that part of it if you had the 4802. But it's clear now that those signals come from circuitry here on the front panel, and you wouldn't have these two boards if you had the 4802 version. So that leaves this main board being the main power supply, the microprocessor circuit, that's probably pretty much this thing here. There are two identical front end circuits. That's for the Y1 and the Y2. And then I'm guessing, without having the schematics and so on, I'm guessing that this area here functions as the trigger circuits and the horizontal sweep generator circuits. That would be my guess. A fairly logical layout. Just divide this board into quadrants: microprocessor, horizontal and triggering, and then the two analog front ends for the Y1 and Y2 inputs. I remember thinking this was a pretty busy kit when I built it. It was the most complicated Heathkit I had built up to the point when I assembled one of these, again, I think in 1987. But it did work really well. I remember thinking that the display didn't look that great when I was driving my analog scope with it. It did work, but I wasn't completely blown away by it, and I only used it hooked up to a computer to capture waveforms for equipment I was documenting, you know, the calibration procedures and things like that on. That was the only use I ever put mine to, and it seemed to me that it did a pretty good job of that. So I don't think I can really go more into the weeds on it, except to note that, you know, the two front end circuits here for the analog inputs, instead of having a great big selector switch with a bunch of attenuation resistors and compensation trim capacitors, that's being done by relays on here, a bunch of tiny little relays. And considering that, let's see, well, certainly these relays here are for the one channel and those are for that. There's what appears to be an extra relay, this one here in the middle, and I'm not sure what that does offhand. And then certainly, you know, these resistors here, probably these two banks of resistors are your input attenuation for all the different voltage ranges, and the trim capacitors you expect to be in that area are there. And then you've got, you know, probably some op amps and some other stuff in here. I would expect that the analog to digital conversion is going on in something over here. I'm not sure what. That's about as far as I can guess on this. When I was going over the circuit board earlier, I made a small error up here in the upper right hand corner from this perspective. As I said before, this area here is the microprocessor. It's a Z80 processor. It's a 8250 UART. There's the RAM chip right in the middle of the screen, and the ROM chip in the middle of the screen with the label on it. Copyright 1984. And then all the support logic and stuff around it. The crystal is way over there in the corner. So there's that. There's a lot of LM374s, and those are either buffers or latches or something, 8 bits each. And that's just to spread out the buses. The Z80 can directly access the UART, the RAM, and the ROM in memory space, but to reach out to any other devices besides those, it has to go through these various buffers and or latches. And I was correct before when I said, of course, you've got the two analog channels here for the front end. But what I'd said over here, which was done without much thinking, was that this is the sweep section. Well, it is involved with the horizontal section, but there's no sweep on this. A traditional scope sweep circuit is generating a signal that increments so that it can drive the CRT beam from left to right on the horizontal axis. You're not really doing that with a digital scope like this. Instead, this is really the triggering circuit that deals with triggering in the various modes this scope can be in. So that's really the preponderance of ICs in that area have to do with the very elaborate triggering circuit. So that's my correction there. Just another tidbit is that on the front panel logic board, the vast majority of the ICs on there are kind of like these ICs here. They're 8-bit buffers or 8-bit latches, and they're all addressed in I/O type of memory instead of the memory map. So they're considered I/O and addressed as such. And those are mostly directly driving all the LEDs. These ICs do not drive the front panel switches, although one of them does. Somewhere on there, probably that last IC over here, that might be the one. It's a quad tri-state buffer chip, so it wouldn't merit one of these bigger packages. And what that's doing is taking 3 of the address lines, buffering them, but with a tri-state control, so they're only allowed to influence anything at certain times, and then those drive all the front panel switches in a matrix. So it's like 3 rows with up to 8 switches per row in the matrix. So that's happening with one of those ICs. And the other thing that's on here, and I believe it's just this area right here that I'm hitting with my flashlight, is there is a D to A converter on there. So that it's also mapped in as I/O, so the processor can send data to that, have it converted to analog. That smaller chip is an op-amp, and then probably, well, one of those 2 chips down there is the D to A converter, 8-bit D to A converter. And its output is a current type output, so the op-amp converts it to a voltage. And then there's the calibrate trim pot for that, and then it leaves with that orange wire, and it snakes down under the board. And that's going to the vertical output jack there. So that drives the, if you connect up an analog scope, that's what's actually sending the vertical signal to the vertical input of the analog scope. Then one of the various latch chips on here, one of the bits is used through a transistor. It's kind of hard to see under there, but somewhere there's got to be a transistor on this board. There's a couple of them there that operate the trigger output, which is just a digital signal. And there actually are 3 voltage regulators on here. I think I said there was just the one, which is down there. You can kind of see its hardware bolting it to the bottom of the chassis for heatsink. That's a 7805, so that handles all the logic on this board. And it also powers all the LEDs on the front. But somewhere on here, and it might just be actually those 2 things I pegged as transistors before, which are just really hard to see. Over there. Those are probably actually the plus and minus 12 volt voltage regulators, which are used by the digital to analog converter circuit over here. So those are actually the plus and minus 12 volt regulators. The low power version that is just in a small transistor package. But there's got to be a transistor on here somewhere that I'm not seeing. It's probably under the cable that is driving that trigger output. Otherwise, I don't have any revisions to make to what I said before. Alright, I have the ID-4850 connected up again to my signal generator or function generator, both channels. It's getting a sine wave and a triangle wave at different amplitudes and frequencies The front panel is active, and it's connected up with an RS-232 cable to this old Windows 7 computer running the current Windows version of the Scope software, which is the Gary Appel dated 2023 revision 1.1. All the settings are over here on the right for the Y1 channel, the Y2 channel, the sweep, the trigger, and status about whether it's triggered or not, whether it's currently transferring. It isn't real fast, but I am getting my waveforms there, and you can see they're at different frequencies. If I were to set the amplitude correctly, oops, that's the wrong way. There we go. I've got a little glitch in channel 2. I'm not sure where that's coming from, if it's the software or if it's something in the scope, but it's basically doing what it's supposed to. It's like it's sampling incorrectly or something. I'm not quite sure what's going on, but it's basically doing what it's supposed to. I'm not trying to actually use this for anything. Wonder what would happen if I change my trigger to Y2, if that would make any difference. That's a little clearer. It's not corrupted now. So yeah, it's working. The blue trace is channel 2, as indicated here. The red trace is channel 1, as indicated here. The voltages are indicated, and the sweep time is indicated here. So pretty straightforward. Now I can show that the controls here influence the controls there. So as I'm over here on the computer changing the AC-DC coupling, for example, I go from DC to ground, and you could see that one LED changing position down there in the lower left. Channel's turned off. AC coupling. To ground. And to DC coupling. And I'm going to go over here and change some of the voltage settings so you can see that happening. I'm going from 1 volt to 2 volts to 5 volts. I'll go in the other direction. Alright, so that's the way that works. And if I change it down there, it'll change up here as well. So I'd say that's working perfectly. There was a little issue with the triggering on the one channel that I have some offset put in here, positionally speaking. You can see they're not both zeroed or centered on 0. If I switch to AC coupling, oops, there we go. Wait for an update. I'm not quite sure why I have that offset there. If I've got AC coupling, it should be straight through. Maybe my positions aren't what I think they should be. I'm going to center the position here by pushing both of these buttons at the same time, making sure that the vertical position is centered. See if that helps at all. No, it doesn't. I don't know why that is. Or actually to ground, that's what I should be doing. Okay, both traces should be centered, and you can see there's an offset. There may be something on the scope where it needs to be dialed in for DC offset. I'm not going to mess with that. Anyway, let's get it back to the point where I have a trace on here. Wait for it to do an update. Boom, there we go. So it's working. I'm just using the same USB to serial adapter that I use when I'm talking to my my Altair computer over here. So I didn't install anything new. I just connected up my RS-232 cable from the end of that across the room to the back of the scope and plugged it in, and it worked. I wasn't sure if I needed a null modem cable or what, so I just took a chance that I had it right, and if I had to I could swap the transmit and receive lines, but it worked the way it was, so that's nice to know. Alright, I'd gone into control here and selected the external scope off. That's supposed to turn off the part of the scope that controls this, and by doing so get a higher speed transfer rate from the scope to the software here, and that does seem to be the case. I'm getting somewhat more frequent updates, although right now it looks like it's sine waves on both channels. And I meant to go to a ramp wave on this guy. So on the next update I should get a ramp, hopefully. Yep, there we go. The red trace is now a ramp. Let me go to... Yeah, that's a little nicer. So if I click the button here, the time is... You can hear the scope click right now when I click it. So that was pretty quick. Anytime I change it in the middle of a transfer, I get some corruption on it. But the rest of the time I'm getting pretty clean readouts. Yeah, so it's basically working. I would not want to have this as my primary scope though. Definitely not as nice as using a real scope. Alright, about the only cleanup I did on this was just going over the case with isopropyl alcohol, using some touch-up paint on the places where the paint was scraped on the black parts, because I could match that color, cleaning the power cord, cleaning the front panel, soaking the outer case in warm soapy water and scrubbing it down, but I can't match the paint color within reason, so I'm leaving the few very minor blemishes on that alone. And really it doesn't need any other restoration. I'm not going to go through the calibration on it because I'm never going to use it, but it's nice to know that it's working. Alright, here's the power-up sequence. See if I can keep the camera on it as I turn on the power in the back. The power switch is in the back. So you can see all the LEDs scrolling there. And then it settles on its default positions, and you can hear all the internal relays clicking into the positions that are appropriate for those settings. Alright, there's the beauty shot. Alright, I'm going to do the quickest walkthrough of the manuals that I can. These are very large manuals, but I don't want to take too long on them. I just received these today from manualman.com, and it's actually in 3 parts, and I only got 2 of the parts. I got the complete assembly manual and the text part of the operation manual, but I'm still owed the diagrams part of the operation manual. For some reason, he was not able to ship that along with the others. Maybe he had an equipment breakdown or something, but he knew I was waiting on these, so he hustled out the parts that he could get out. And I should mention that I always order these without binding because he doesn't do bindings the way I do, and I prefer the way I do it. So I always order them without binding and put my own on. So this is again very late Heathkit, 1986. And they were out of business just a few years after this. At least out of business in terms of making most of their kits. So this was very late days. There's a lot of indications in here that they're already falling off. Not necessarily in the design department, but in the documentation department. The schematics are very poorly drawn. You know, they didn't put a whole lot of effort into those, for example. And I vaguely remember thinking that the assembly manual wasn't as good on these as what I was used to. So, introduction. Heathkit Digital Memory Oscilloscope, otherwise known as the DMO for short, model ID-4850, is a versatile accessory for an oscilloscope or PC-compatible computer, such as the Zenith Z100 PC series. Now, of course, Zenith owned Heathkit at this time, so of course. Or the Heath H100 PC series or an IBM PC. It can upgrade an oscilloscope that has a low frequency bandwidth to a 50 MHz bandwidth on repetitive signals, and can also add waveform storage capabilities. When you connect the DMO to a computer through its RS-232 connector, the supplied software provides you with full control of the DMO functions from the computer keyboard. The waveforms are displayed on the computer screen. The computer software also provides you with the added capabilities for disk storage, averaging, and cursor measurement of voltage, time, and frequency. User-written software can also be used to customize the DMO for specific applications, such as automated testing. The DMO is a sampling oscilloscope. It periodically samples analog input signals, converts them into a digital code, and then stores them in its memory. When these coded signals are retrieved, they are displayed as waveforms on the oscilloscope or on the computer CRT. The DMO samples repetitive signals from 0.4 seconds per sample, I think that's what that is, to 200 picoseconds per sample. I think that's what it means. They didn't really explain the units here. And non-repetitive signals from 0.4 seconds per sample to 100 microseconds per sample. Yeah, so that's what that is. Seconds, picoseconds, and microseconds. The attenuator networks for channels Y1 and Y2 have 10 calibrated ranges from 5 millivolts per division to 5 volts per division, and are switched in a 1-2-5 sequence. The calibrated time base ranges from 20 seconds per division to 10 nanoseconds per division, also switched in a 1-2-5 sequence. The trigger select and trigger level allows the time base to be triggered at any point along the positive or negative slope of either the Y1 or Y2 trigger signal. And I think that factors into what I'm going to talk about later, where there's a ramp signal, and I think that's what that was emulating, was the normal horizontal sweep of a traditional oscilloscope. An auto baseline function is provided to automatically display a baseline on the screen when there is no trigger signal present. Some of the features when you use this unit with a normal oscilloscope include 2.5 Hz to 100 kHz real-time sampling rates on non-repetitive signals, 50 MHz bandwidth on repetitive signals, 7 nanosecond rise time on repetitive signals, single sweep function, 5 millivolts per division vertical sensitivity, waveform storage, comparison of live versus stored waveforms. Some of the features when you use this unit with a computer include control over large distances via RS-232, control via a modem, signal averaging, inversion of either channel, cursor measurement of voltage and differential voltage, cursor measurement of frequency, time, and time difference, waveform storage on disk. This digital sampling oscilloscope is a laboratory-grade test equipment ideal for the wide range of measurements used in electronics equipment education, production lines, and scientific research. So there's a million pages here for assembly, so I'm just going to sample a few of them. It does start out with the normal Heathkit stuff, you know, the tools that are required, tips on soldering, how to identify resistors and capacitors. Starts out with the simplest circuit board, the display circuit board. Doesn't have all that many parts on it, or if there are, they're repetitious parts. Heathkit by this time was supplying most capacitors, the small ones, and all the resistors as taped components. So they were ordering them from the resistor manufacturer taped and in pretty much in the order they were going to be assembled. So that simplifies the instructions quite a bit. It's just take the next resistor off the tape and stick it here. So step-by-step instruction, mounting the little switches on the boards, mounting the LEDs, and there's some little LED spacers they included to get them mounted properly. Putting the little buttons on the tactile switches on the circuit board. Now we're done with that, and putting on the connectors. The display logic circuit board. It has more parts, but again, it's mostly the same parts over and over again. Step-by-step assembly. Notice that there aren't as many pictures as you might expect here. That's because those are done on fold-out diagrams instead of being right on the pages of the manual. But there are still some details for mounting IC sockets, potentiometers, resistor networks, and so on. The main circuit board, this one has a whole bunch of parts, pages and pages of parts. All those ones so far were non-taped parts, and these are taped parts. So it was resistors, axial lead, ceramic capacitors, diodes, all that stuff, step-by-step assembly. It's mostly just the check boxes because you're supposed to be referring to the diagrams that are folded out. So it's just lots of pages of check boxes and what goes where. So I'm not going to dwell on that too much. But the diagrams are pretty consistent with Heathkit standards. It's really just moving most of the big diagrams to the fold-out diagram sheets instead of embedding them with the text. Then the chassis assembly. It's not really that complicated, but there is some wiring. Initial tests, preliminary wiring checks, voltage checks, installation of the ICs. There's a lot of ICs on here to get burned up if you didn't do the power supply or the wiring right. So that's why they were being cautious before installing the expensive parts. Final test. and setting all the trim pots to preset positions. Final assembly. And then we get into the description, or the diagrams. Circuit board diagrams. These are component identification diagrams here. Come on. Looks like there's a bit of a bodge on there. One place there's supposed to be a diode tacked in. More circuit board diagrams. So it's like one diagram focused on ICs and trim pots, another one focused on resistor networks and things like that. One of them focused on the relays and transistors. One focused on most of the capacitors and voltage regulators. One focused on several of the ICs. Parts identification. Wiring up things like the RS-232 jack and the power transformer. Mounting heat sinks and things to the back panel. Various shielded cables. A test point diagram. This is a parts location diagram for all the ICs on the two boards that have ICs. Front panel and connection of that, or the front panel cables, two shielded cables and the ribbon cable. There's apparently a test cable that came with it that you had to build. Some details on the front panel. Then this is all the adjustment points here, identifying all the trim pots and the jumpers. And then it has diagrams for all the different taped components drawn to scale. That's just single-sided. Yep, and that's the end of the manual, except for the inside back cover, which has instructions on ordering replacement parts, technical consultation, and repair services. Alright, here's the operation manual. A little bit smaller than the other one, but it's still going to be pretty involved, I think. Table of contents. It's a little different from the one on the other manual, but I think it's going to say basically the same thing, so I won't go into that. It does have specifications, vertical and horizontal. Accuracy of the vertical is, let's see, input impedance is 1 mega ohm. Accuracy within 3% plus or minus 2 bits, so not terribly accurate. This is not a great scope for doing precise measurements. Actually, no scope is, but unless you've got the cursors on them that can help you with that, but if you're just doing it visually, they're not that precise. And this is less precise. The resolution is not good. It's only 8 bits of resolution on the sampling. Trigger source, it can be channel 1 or channel 2. Coupling is the same as the vertical input. The modes are automatic baseline, normal, and single sweep. Level is variable over at least 8 divisions, 256 steps. The output of the oscilloscope is 4 volts peak to peak. The oscilloscope setting that you're connecting up to is 0.5 volts per division vertical and 1 millisecond per division horizontal in order to get the signals being generated by this equipment to look right on that screen, and the trigger is TTL level. System requirements for your computer that you would have connected to this: MS-DOS and GW Basic. Although you don't need the GW Basic, as I recall, you could use it. There's an EXE furnished, and that's the scope software, and that just runs in DOS. And then there's the GW Basic, which is what they developed their scope program in. And I think the EXE file is just a compiled version of that GW Basic program. So if you want to go in and hack the code, you'd need GW Basic or something similar. PC compatible computer with an RS-232 card, color graphics card, single 5¼ inch disk drive, 128K RAM minimum, such as the Heath Zenith H/Z100 PC series computers. GW Basic is not required to run the compiled version of the scope programs. You can use the DMO with any computer that has RS-232 serial communications and graphic capabilities if you develop your own required software. General vertical resolution is 8 bits, 1 part in 256. Record length is 512 samples. Interface RS-232C. Baud rate 110 to 9600 baud, selected by internal jumper. Power supply is fully regulated. Operating temperature 10 degrees Celsius to 40 Celsius. Power requirements 108 to 132 volts AC, 60 hertz. There seems to be no option for running it at 240 hertz, although or 240 volts. I don't think the frequency makes any difference. It's a linear power supply. Probably would work okay. It weighs 8 pounds. Other equipment needed. This is, if you're going to use it with an oscilloscope, this is the minimum requirements for the scope, and if you're using it with a computer, minimum requirements for the computer. Getting started: using your DMO with an oscilloscope. Using your DMO with a computer. Controls and connectors. Spells all the controls out here. Internal jumpers. And there's some pictorials such as setting the baud rate. Now, with mine, because I didn't have the manual and there were already jumpers installed, and I didn't know what they meant, other than some of them were marked for baud rate, but the software I was using was only 9600 baud, and it was communicating, so apparently whoever built my scope set it for 9600 baud, which you'd want to under most cases. Why have it be slower than necessary? Connections to oscilloscope and or computer. Using the keyboard, like you can invert the traces and things like that from the keyboard. There's some menus in the software that are described here. Normal operating characteristics. Using a 5 millivolt oscilloscope. Operating characteristics of a digital oscilloscope. Real-time sampling. The DMO uses real-time sampling techniques on the time base ranges between 20 seconds per division and 500 microseconds per division. Real-time sampling is a system that, once triggered, takes a series of equally spaced samples of the input signal. One limitation of this type of system is that changes in the signal that occur between samples is lost. This loss of information is referred to aliasing. A measurement technique to avoid aliasing. The input circuits of the DMO have a bandwidth of 50 MHz, but input signals up to 100 MHz reach the digital sampling circuits. A mathematical theorem called the sampling theorem indicates that aliasing does not occur if the input signal is sampled at least twice per cycle. One cycle at 100 MHz is 10 nanoseconds. If you wish to sample each cycle at least twice, you must take a sample every 5 nanoseconds or faster. If the time base is set to 200 nanoseconds per division, a sample is taken every 4 nanoseconds, and aliasing does not occur for input signals with frequencies less than 100 MHz. This is the key to making alias-free measurements. Equivalent time sampling. Now, I've already touched on these things in my discussion in the schematic, and I'm doing this before that, so it's kind of backwards. The DMO uses equivalent time sampling techniques on time base ranges between 200 microseconds per division and 10 nanoseconds per division. The major difference between equivalent time sampling and real-time sampling is that, while real-time sampling may be used on any type of waveform, equivalent time sampling is only useful on repetitive signals. This is true because the equivalent time sampling technique takes only one sample each time the oscilloscope is triggered. Since the DMO takes 512 samples of the input before it is displayed, it must get 512 triggers if it is in the equivalent time sampling mode. So that is probably a clearer way of describing what I'm going to go over later when I go through the schematic and the theory of operation. So what they're saying here is, if you're reading slower signals and you've got, a waveform here, the circuitry and the logic and the microprocessor is able to keep up with taking samples in real time. So here's the waveform, and it's taking, if you break this up into 512, it takes samples at all those points. But as the frequency gets up higher, it can't keep up with it anymore. So what it's actually doing is, here's the waveform again, and this is a fast waveform. So what it does is it takes one sample, like here, and then it waits for another trigger, and say you have the trigger set when you start having a positive slope up from 0 volts. So it's always triggering at the same point, but for this to work, the waveform has to be exactly the same 512 times in a row. That's what they mean by repetitive signals. And then a little bit later, on the next sample, the next time the waveform recurs, it takes the sample a little bit later. And the next time it's triggered, it takes a little bit later, and so on. So it accumulates the samples, one sample per occurrence of the waveform, one cycle. And that's how it's accomplishing that. And that's just so that it can keep up. This will make the other part I'm talking about make more sense when we get to it. And that's why there's a big time limit in the specifications if you're in real-time sampling, that you can't go up to the full rated 50 megahertz of the scope. Digitizing errors. There are only 256 digital levels that may be used to describe the input waveform. Operational examples. Lots and lots of those. Examples of using the memory, saving to disk, service information, calibration. This is how you can calibrate it. You can calibrate it if you have another oscilloscope. Doesn't have to be a storage one. Lots and lots of adjustments on here. Calibration using a computer. Then we get into the in case of difficulty section. Theory of operation. And that's what I've already printed out. I printed those out separately from a downloaded version of just that much of the manual that I found online. But that's obviously the same thing here as, except it's easier to read here. The scanned one I looked at was kind of washed out and a little hard to read sometimes. So this is much nicer. Manual Man always does a nice job. They use really clean originals and then they clean them up further, I think. So there's a rough circuit theory overview and then the in detail section. Lots of pages. Then we get to the replacement parts list. There's a lot of parts, so a lot of pages of that. Organized by which circuit board they go on. And then semiconductor identification. Number of pages of that. Lots of different ICs. Lots of different ICs. Holy cow. Commands and responses. This is again regarding signals you send to and from the scope and things like that. What address various things are at. You know, for example, if you're trying to turn on an LED, what data you have to send out to a particular address in order to get a certain LED to turn on. And the same thing for the horizontal and some of the other indicators. How to make a backup and or working copy of the software. All this stuff is really outdated unless you have a DOS computer. And then that's the end of the operation manual, excepting the diagrams that I don't have yet. Alright, I'm going to take a crack at going through the schematic. I'm not going to dwell as much on the fine points as I usually do in my other test equipment videos, just because this is a large and complicated circuit and this video would go on for many hours if I tried to do it that much, but I'm still going to try to cover a lot of it. Now, the first part of this is going to apply to more than one model of instrument. The IC-4802, which is the scope that's only a computer scope, and the ID-4850, which is the subject of this video, share the same basic case except for the front panel, and they share the same main circuit board. So all the features that are common to both models are on the main circuit board, and then anything that's additional on the 4850 is found on the two front panel circuit boards. So again, this part of it here will be pertinent to both models. This schematic page here is primarily the digital portion, and it starts out with a microprocessor, and this is a Z80. It has a lot in common with the 8080 on which it's based, except it has a number of refinements, extra instructions, and some things that are just done nicer, if you will, cleaner. It doesn't require the auxiliary chip that generates the extra power supplies and clock signals, for example. So there's a lot of improvements. Around the Z80 microprocessor, we have to have a clock, and this is the clock circuit here. It's crystal based and uses a transistor, and there's a few other things around it which I won't go into, a lot of capacitors and such that are there for voltage stabilization. And it puts out an 8 megahertz clock, which is then brought down here to this pair of flip-flops. The first one divides that frequency in half, so you end up with 4 megahertz, and that's brought up and used as the clock by the Z80. And then that same 4 megahertz is divided in half again to make 2 megahertz, and that is what is used by the UART, which is the serial interface IC that handles all of the busyness that deals with serial communications, so the microprocessor and its software doesn't have to deal with it. There are a couple of signals involving the read and write instructions coming to or from the Z80, and for certain things we need to delay the read instruction or the read command, the read signal, whatever you want to call it, and the write signal for certain situations. And that's done with another pair of flip-flops so that the signal is sent to the flip-flop, but it only gets through the flip-flop on the next clock cycle, thereby slightly delaying it. And that avoids some problems downstream in the logic that I won't even try to go into here. It would take too long. Just suffice to say that there's a little bit of that going on. While we're on the subject of the UART, it does come out with handshake signals to the RS-232 connector. It has the normal transmit and receive lines, the TX and RX. It also has the DTR, the DSR, the CTS, and so on, the RTS. And so there's 3 signals going out and 3 signals coming back in. A 1488, also called a 75188, it's an RS-232 driver IC. So 3 segments of that convert the TTL level signals coming from the UART into the appropriate plus and minus voltages that the RS-232 standard expects. So it's in full compliance with the specification. And then the signals coming back in are plus or minus 12 volt signals. And the companion IC, which is the 1489, otherwise known as the 75189, again has 3 segments that convert those signals into TTL level signals for use by the UART. So let's step away from the UART and go to the power supply. Probably should have done that first. It's a simple power supply. It's all linear, very straightforward, nothing cute about it. I've only got the secondary, the power transformer shown here, but on the primary, it's just the power cord and a power switch, and then the primary winding. So we have 2 windings with center taps. One of them is 9.5 volts across the outer 2 ends of the winding. The other one's 16.5 volts. These are brought in each with their own full wave rectifier relative to the center taps, which are grounded. So you end up with a 2 diode full wave rectification coming off of the one side of the winding, and then another 2 diodes for full wave rectification coming off the other side of the winding. And that gives you a plus and minus 9 volt approximate signal after filtering. That's off the 9.5 volt winding. And then there's a 7805 and a 7905 linear regulator, which knocks that down to a regulated plus 5 and minus 5 for use everywhere on the main board that needs those voltages. Likewise, the 16.5 volt supply has exactly the same kind of circuit, but it uses 7812 and 7912 regulators to end up with a plus 12 and a minus 12 regulated power supply. Going back to the processor, there's a few other little nuances around here. There's, decoupling capacitors and so on, but basically you have a lot of control signals, halt and memory required and I/O required, keeping in mind that both the 8080 and the Z80 handle memory separately from I/O. You can have memory mapped I/O, but the original design of these ICs would have had I/O totally separate from memory, so it has separate signals coming out. And then there's the read and the write like you'd normally have. And there's a bus acknowledge which is one of the things that can cause the microprocessor to give up control of the bus under certain situations. There is the wait signal, the bus required signal that goes in with what I talked about just a moment ago. There's reset and a signal called M1. I don't remember what that does off the top of my head, and some other signals. But then, of course, it has the 8 data bits making up the data bus and the 16 address bits making up the address bus. The address and data lines go directly to the ROM IC and to the RAM IC and to the UART, although the UART only uses a few of the address lines. It also goes to this hex buffer here, so it passes 6 signals through it coming off the data bus, and those go to a set of jumpers on the circuit board, which are used for configuration. 3 of them are used to set the baud rate. One of them is used for calibrate versus normal mode, and there's a couple called hold off, which I don't know what those do off the top of my head. Some of the address lines go to this memory decoder, so it's 3 address lines along with the memory required and RFSH and some other things, and it all gets knocked down to one of 8 outputs. So depending on what those upper address bits are, it'll select that the ROM should be enabled, or the RAM should be enabled, or we should look at the jumpers, the ones I just mentioned, or we also have the start analog to digital conversion signal. So there's 4 things that are in memory space that are decoded using this IC. So you'll notice that the ROM output enable goes up and goes into the ROM to turn that IC on, and likewise for the RAM and the other things. Now, some other address bits are used by a similar IC. It's actually the same kind of IC as the memory decoder, and this is the I/O decoder. It has 2 signals dealing with the 2 channels, the EQ control, the EQ range, the trigger level, the EQ staircase, so-called, the analog to digital, and the UART. So these are all treated as things that are handled in I/O space instead of memory space. So the UART signal comes back around and goes to the UART, and I should mention that the UART can be controlled 2 ways. It's on the data bus, and it has the address, some of the address bus going to it, but when it's being used actively, it's treated as part of the I/O space. But sometimes when the processor is not trying to deal with I/O, it's doing other tasks. If a signal comes in from a connected computer, and that's what the RS-232 is for, to connect this to a computer, if the computer is sending something to the scope and the UART detects that and says, hey, this needs to be given priority attention, then it's able to be accessed through memory space instead of I/O space. So there's provisions for it being accessed in certain ways in both of those memory and I/O areas of the processor, if you will. This is just some glue logic down here for combining signals in various ways. And then down here is the main analog to digital converter that brings in the 2 channels, but I'll get back to that later. Suffice to say that it's connected up to the data bus so that the analog signal coming in can be read by the microprocessor. Now this IC here is connected to the data bus, and it's an octal bidirectional transceiver. So on the other side is another I/O bus, but this is the I/O bus related to the data bus. So it's a special version. It creates a special version of the data bus just for use by I/O on the front panel. So it's tri-statable, and it's also bidirectional. It can be set up to send data from the data bus to the special I/O data bus, or it can be set up to send things from the I/O data bus back to the data bus. So that's its function. It's to interface the digital logic on the front panel, at least the data bus part of it, so that it can go off board and be used by the two boards on the front panel if that is connected. Now the I/O decoder down here, I already mentioned that it has various signals coming out of it, and the majority of those go to these 6 octal latches. 1, 2, 3, 4, 5, 6. They're all connected up to the I/O data bus, so also coming off of this IC, because these are all working in I/O space instead of memory space. And each one of them has a chip enable, which is in turn coming from the I/O decoder. So at any one time, one of these 6 latches can be connected up to the I/O data bus, and thereby through this chip to the actual data bus. And that's all for controlling all the things on the rest of the board that need to have digital control. There's quite a few things that are going on. There's a lot of signals here that are coming out of this IC and this IC. These are all operating like all the little relays on the circuit board, which do all the range switching and so on. Each of those is buffered by an IC to give them more driving power, because these points here are all going to coils of relays, and then they leave this sheet and go off to another sheet. But that's how the relays are driven, from these 2 ICs and their signal buffers. This one here is primarily the EQ control, and the EQ is for equivalent, I forget what they call it, but it's one of the 2 modes of bringing in signals. The scope has 2 different ways of handling signals depending on their frequency and what other selections you've made on the scope. So this chip primarily handles circuitry having to do with that equivalent mode. This chip primarily handles signals dealing with the trigger level controls of the circuit, also on the same circuit board. So all of its signals go off this sheet. This one has to do with the equivalent range, also leaving and going off the sheet. And this one has to do with the EQ mode staircase signal, which will be talked about to some degree a little later in this video. But so that's where all those signals are coming from, this whole bank of octal latches, all being driven from the I/O data bus. There's a signal that's derived back over here called EQ SAM, and there are 2 monostable multivibrators here and here. They're the same kind. They're actually 2 halves of one IC, and what they do is they take a brief pulse and then through the use of a resistor and a capacitor convert that into a pulse of a specified length. So this one monostable generates a 2.5 microsecond pulse, which is used, one of the complementary output of that gets fed back, and it gets used with some of the glue logic over here. Again, I can't take all the time it would take to explain what it's actually doing. And the non-complemented output of that 2.5 microsecond gets sent up to the other monostable, and it's used as a trigger here, but it also is conditioned by the start A to D signal from the memory decoder. So when the processor's trying to start an analog to digital conversion, it relies on combining that signal with the 2.5 microsecond signal coming from down here. And when those two are true, then this guy generates a 1 microsecond pulse, which is again wrapped around, goes way back over here, and gets combined with some other stuff in a particularly important way that would take way too long to explain. So that's essentially what's happening on the digital logic part of the circuit. You end up with a whole bunch of signals going to control relays. You end up with signals that control the analog to digital conversion, the sample and holds, the signal coming from the front-end circuitry going to the analog to digital conversion, the channel select signals, all sorts of things, all going off to logic on another sheet of the schematic. Here's sheet 2, and this is one of the biggest abortions of schematic drawing I've ever seen. They were really trying to jam way too much stuff in to one drawing, and things are just drawn one on top of another. There's no care given here whatsoever to laying it out so it makes sense. And there are some places where parts of one section of a circuit are drawn on top of another section of the circuit, with the parts all just mixed together, even though they're in completely different parts of the circuit. It's enough to make you pull your hair out. I spent hours trying to dissect this and make it make more sense, and it's very difficult. So to that end, this is really the same thing twice. This whole section up here, and this whole section down here. This is for channel 1, this is for channel 2, and then there's a little bit down in the middle that's common. So I redrew channel 1 on another schematic. Now I didn't pretty this up, but it still makes more sense, and it's full of my notations, so it's kind of a cluster, but at least it's laid out without things being on top of other things. So again, I'm going to have to kind of kiss through this thing, just keeping it simple. I'm going to skip over a lot of the nuances. But here's a typical input BNC connector. It's on the chassis. It connects up to the main circuit board through a 2-pin connector. There's a 51 ohm, I think, resistor. A lot of the resistance values on the schematic are just totally illegible. So I was taking my best shot at what their values might be. And here's a relay. This relay is associated with the AC, DC, off and ground selector, but it's a single relay. It's basically picking AC and DC. And so if it's in AC mode, this is your coupling cap here, which only lets AC through and blocks DC. And if you short the capacitor out, then it's in DC mode because it'll pass anything. So depending on whether the relay, so if you have the relay in this position, this is the default position when it's not energized, it's shorting out this 1 meg resistor, but the signal must go through the capacitor, therefore it's in AC mode. If the relay is, however, energized, now any signal can get through it because it doesn't care about the capacitor, so AC or DC components of a signal can get through it. We have 1, 2, 3 relays here. I didn't show the coils on these. You just have to know that there's a coil for each with a diode across it because it's a DC coil, and that's what you do to cut down on noise. And those relays are all driven by those signals I already mentioned. This one is the divide by 1, the divide by 10, and this one here, which doesn't really have a name penciled in, but I think it's the divide by 100. So it's a order of magnitude prescaler. If the relay's in its normal position, it's going to ground each case. And then there's sort of a bus over here, which is common to all of them. So for example, if the relay that I'm calling divide by 1 gets energized, it's taking that input signal, bringing it through, and sending it off downstream. If the divide by 10 was, then the input signal would go this way and go through a different attenuator circuit. And if the divide by 100 is energized and closed, then the input signal goes through the divide by 100 attenuator. The logic has it so only one of these will be operated at a time. So if we're in the divide by 1 mode, there is no real attenuator. There is a trim capacitor here, which should be dialed in during calibration, but it's not really attenuating anything. In the divided by 10, we have also a similar trim capacitor, and then we have a voltage divider. It's basically 900K over 110K, but that ends up being your divide by 10. And then there's a high frequency bypass around the upper resistor with a trim capacitor on it, so that can be dialed in for best response at higher frequencies. And then there's a resistor and a capacitor to ground, and then it comes on out. That's the divide by 10 attenuator. If you're in the divide by 100, it's a very similar structure. In this case, it's 990K over 10.1K with a high frequency bypass around the upper resistor, RC to ground, and so all three signals are brought up here. This relay is in its normal position, so if we don't energize either of these two relays, then it's the divide by 100 signal that makes its way to the input circuitry over here. If you were to energize this relay up here, then it'll take the signal coming from the divide by 1 relay. If you energize this guy, it'll take the signal coming from the divide by 10 relay. So that's how the rough attenuation is accomplished in orders of magnitude. Now we have, from this point to this point, a 499K and another 499K in series. It's a voltage divider, and those together make up approximately 1 mega ohm. This establishes the input impedance of the channel on the scope as 1 mega ohm, which is pretty common. Now things get a little more interesting here. Basically, the signal just goes sailing through this capacitor here, so it's AC coupled, and it goes into the high impedance to low impedance translator circuit. But sometimes over the entire frequency range of the scope, especially at low frequencies, this capacitor starts messing with the signal too much. So there's a provision here to bypass it. We take the divided in half signal coming off of this, we run it through an op amp, which has negative feedback, and then that's brought over here. So low frequencies are more or less blocked or partially attenuated by this capacitor, but at lower frequencies, then this circuit becomes more active, and it starts, the signal coming out of the op amp is overwhelming the signal coming through the capacitor. So you have two different paths, the higher frequency path and the lower frequency path. And then that's presented to the impedance translator. This is a fairly classic circuit. It's just kind of messed up the way I drew it because I've got all the notations around it, and it was my first crack at deciphering the mess that was the original schematic. But basically, we just have a traditional FET front end here. It's a source follower, very, very, very high input impedance. So compared to its impedance, none of the impedances over here mean anything. So this doesn't load those down at all. It's essentially taking the measurement without messing up the thing it's measuring. For best performance, a source follower FET like this needs a current source, or a current sink in this case. And so there's this transistor here that's providing that path. And this is a power rail here. It's generated off the minus 12 volt power rail with a Zener diode, and it creates a minus 6.2 power rail, which in turn gets divided in half by this voltage divider and filtered, creating a minus 3.1 volt power rail. This is considered a stable voltage, and it's applied to this transistor's base. And if you hold the transistor's base constant at a constant voltage, then it acts like a constant current source or sink. So there's always a constant current coming out of the FET and then through a resistor to that minus 6.2 volt power rail. And that again is used to make this source follower work optimally. This by itself has a low output impedance, but to get an even lower output impedance, that signal coming out of the source is current amplified by this transistor here. It's another emitter follower, or it's an emitter follower following a source follower. And it's just connected up to a positive 6.2 volt rail, which is created in the same way as the minus one. A plus 12 volt with a 6.2 volt Zener creates that 6.2 volt power rail. So the signal comes out of there, and that's now a copy of the input signal but with much lower impedance. Now to protect the FET, it has an internal diode functionality between the gate and the drain, so if the voltage here is too high, it gets bypassed around the guts of the FET to the power rail and thereby clamps it to 6.2 volts and nothing gets damaged. But that internal diode doesn't help us with all this other stuff, so it doesn't help protect in the negative direction. So there's another FET here, and the way it's wired with no connection to its drain, just the source to the gate, it acts like a diode, and it's essentially doing the same job as the internal diode here, but in the other direction, clamping the input to no lower than minus 6.2 volts. So that's what's going on there. Now we want the analog section to be as accurate as possible, so we take this voltage that we've conditioned here and we feed it back around to the negative input of this op amp that I already talked about, that's providing a low frequency bypass for the coupling capacitor up here. By doing this, especially at low frequencies, we've created a servo feedback system, so better linearity, better performance. Now that the input signal has been conditioned by all that other stuff, we have some more attenuation that needs to take place. After all, there's more input sensitivity adjustments than just 1, 10, and 100. So we have some more relays here. There's a relay for divide by 1, a relay for divide by 2, another relay for divide by 4 or divide by 10. So 3 relays making a 1 of 4 selection. If we're in the divide by 1 mode over here, the secondary attenuation, then this relay will pull in and we'll just take the output straight off of the emitter follower through the relay and continue on. However, if we need additional attenuation, there's this voltage divider here, and this is a precision resistance divider package. It's one integral device, not a whole bunch of discrete resistors. So it has a 200 ohm and a 100 ohm and a 60 ohm and two 20 ohms in series. So it's essentially 200, 100, 60, and 40. And we tap off between the 200 and the 100 between the 60 and the 100, and between the 60 and the 40 that's made from the 220s. So 3 taps coming off there. If we energize this relay, then we take the tap from here, which in fact is dividing the signal here in half, because it ends up being 200 ohms over 200 ohms. So it divides it by half. Down here, it's 300 ohms over 100 ohms, so it's a divide by 4. So if this relay down here is energized, then we get the divided by 4 signal. If we do not have it energized, then we take the lowest tap, which is divided by 10. So again, combining those with the divide by 1, divide by 10, divide by 100 over here, we get all the different possibilities of input attenuation. Alright, there's an amplifier stage here. It's using a IC that essentially has 5 transistors inside of it, all with matched properties. So it's better performing than just 5 discrete transistors. So there's a total of 1, 2, 3, 4, 5 transistors in that package. And they're set up as a differential amplifier. So it's the classic 2 transistors sharing a common emitter and then going through a current source or current sink and down to circuit common. That's the basic configuration here. It's always best, for best performance with a differential amplifier like this, if you have the common emitter here going through a constant current source instead of, you can just do it with a resistor to ground or resistor to circuit common, but you get better performance if you can have a constant current going there. So these 2 transistors are used to that effect. This transistor is set up to act as a diode, and that is, in this case, it's providing a constant voltage, and that's applied to this transistor. Holding this transistor's base at a common voltage gives you a constant voltage gives you a constant current going from the collector to the emitter here. So that's how this differential amplifier transistor pair is able to function optimally. So whatever attenuation we've selected goes into here, and if this signal increases, then the current through this transistor increases, and there's only so much current that can go this way because it's regulated and constant. Therefore, the current on this side has to be less, and that affects the voltage at this point, which is the output of the circuit. Conversely, if this signal goes lower, then this transistor conducts less, there's less current, and there can be more current going this way, so there's an increasing voltage over here. This is actually used for feedback, so again, this transistor has feedback, and it comes from downstream here. But we also need a little more drive current coming out of this, so the 5th transistor in the package is used as another emitter follower. And this diode down here puts it into a better realm. I won't go into all the details, it just tweaks the performance a little bit. So the output is here, but this is only the output for triggering purposes. This is the channel 1 trigger circuit or signal coming out, but it's not the one that we're going to measure. That signal is coming off of yet a different transistor. There's another emitter follower up here, but it's not made from one of the transistors in the 5 transistor package. It has the same base though, so that same signal that's driving this guy drives this guy. It's also an emitter follower, and very much like this guy, it has this diode down here, then a resistor to the low power supply. And this does exactly the same thing. It has the diode, has the resistor, and it's going to minus 12 volts. So this circuit here is running on plus 6.2 to minus 6.2, but this transistor is running on plus 12 to minus 12. Otherwise, it's the same configuration. There is a trim potentiometer here for high frequency adjust, and then there's a trim capacitor across it with this resistor here, and this is where the feedback is taken from. We tap off here, we come back around, and there's the channel 1 amplifier gain trim potentiometer, and then that's used as the feedback to the other input, the differential amplifier. So this point here is the actual output of this whole circuit that's done, all that conditioning work for the front end of the scope for that one channel. Alright, so we've already started out with the front attenuator section in 2 stages with the amplifier, first stage amplifier, or the high impedance to low impedance translator in between. And then we have the so-called high frequency amplification stage, which I just covered. And now we take the output of that and we come into this stage down here, which looks like an awful lot of parts for what it does. It's a logic controlled device that goes from low impedance to high impedance, essentially. And the whole reason for that is it's a front end to this little stage here, which is a buffer with a capacitor on it. It's a sample and hold, essentially. And now I should point out that everything I'm doing here is just from my own circuit analysis. I have ordered manuals for this and have not yet received them. And depending on when they show up, I might be able to corroborate some of this with the circuit description in the manual. But near as I can tell, there is a need in here. There are several different modes that the scope can be in, and one of them is the real-time mode, and the other is the equivalent time mode, otherwise known as the EQ time. And in those modes, it can be necessary to, instead of taking continuous stream of samples, instead just do a basically to freeze everything and do a snapshot, essentially. And the way that works is the snapshot is held with this capacitor here, so in that sense it's like a sample and hold circuit. So if we allow the amplified signal to come right through this and charge up the capacitor, keep the capacitor charged to whatever the signal is at the moment, it's not a very large value, then the signal just passes right through. But if we want to do a sample and hold, then there's a need to stop the signal coming from the high frequency amplifier and going through here and just hold its latest value in this capacitor. So if we're in real-time mode, then this is a 1 here, a logical 1. This is TTL logic. By the way, it's snowing like crazy outside, and sounds like my neighbors just started up their snowblower. Hope that won't be picked up too much. Anyway, so if we're in real-time mode, the 1 on here just goes right through the OR gate and gets inverted to a 0. And then we have this transistor here. It's an NPN, and with a 0 here, it pulls the base of this low, which turns it off. And because this NPN is on top of a PNP, that's going to turn that off too. If you've got nothing coming through here, then this transistor is essentially off. If this transistor is off, then this resistor here pulls this line high, and going into a PNP, that turns that guy off. So this is off, this is off, this is off. And if you've got nothing coming through here, due to this being off, then this NPN transistor is going to be off. So basically, when you're in real-time mode, all these 4 transistors are off. And now we have these 4 Schottky diodes here. And it all comes down to whether these are forward biased or not. So let's say these transistors here are off. Then you have the top of this, it's like a bridge, is pulled. I've got this drawn in a way which is, I think, upside down. I marked on here that it's minus 12 volts. No, I think I was correct on that. I drew it funny here that this point here is pulled to minus 12 volts, and this point here is pulled to positive 12 volts through 1K resistors. So you end up with, since these transistors are off, the anodes here are at a high voltage, and the cathodes here are at a low voltage, in that sense that they're all forward biased. And then we bring the signal from the high frequency amplifier through here, and because the diodes are all forward biased, the signal can go positive and negative within here, and the diodes are forward biased, so it's, you can almost think of them as being short-circuited. So you know, if it's high, it can go through this forward bias diode. If it's low, then this way, something like that is going on. And these two diodes are basically in parallel with these, so whatever these are doing is what these are doing, and essentially you're going to get something that's pretty close to being a copy of the signal from the high frequency amplifier being present here as well. You know, this is wiggling around, these points are wiggling around, this is wiggling around, and it's presented to this capacitor. And then since it's being actively driven, this capacitor just goes along for the ride, and this op-amp is configured in the unity gain mode, so it's just a buffer. It's non-inverting as well. So for an equivalent time mode, then this is a 0, and if you're not in EQ SAM mode, it's an active low signal. So if you're not in that mode, this will be a 1. And then as far as this is concerned, it's just like if this was in real-time mode and you've got a 1 here. You'll have a 0 here, all the transistors are off, the Schottky diodes are all forward biased, and the signal goes right through them. But now you're in that mode, and now the EQ SAM goes low, so that means that the circuit is trying to do a sample in equivalent time mode. So now this goes low, both inputs are low, therefore the OR solves as a 0, that gets inverted to a 1 by the inverting output. Now all of a sudden we're turning this transistor on. So you've got current going through it. This point is higher than this because this is ground, therefore this is turned on. The current through this provides base current to this NPN, so it's turned on, and meanwhile we're sucking current this way, so that pulls current this way, which turns this guy on, and therefore this rail, instead of being at minus 12 volts, is pulled up to plus 12 volts. And this point, instead of being at nearly plus 12 volts, is pulled down to minus 12 volts. So the polarity of the top and the bottom is swapped, and that reverse biases all these diodes, so they're not conducting. Therefore, the wiggling signal here can't get through to here, and therefore it's like this becomes really high impedance, and whatever signal was last on this capacitor, the charge that was on that capacitor is now frozen, and it's a sample and hold that's in hold mode. And for a while anyway, it doesn't need to be very long, that voltage is just held by that and monitored, buffered by this, and we have that snapshot of the signal here. So I believe that's essentially what's going on there. Alright, the manuals came in just as I was doing this. So I had a chance to flip through the circuit description in the manual. And I had it pretty much correct. Not that I'm going to go back and revise what I said over small nuances. But something I did miss was why some of these capacitors are in here. And a couple of the resistors I didn't mention. One thing is that because this circuit can be operating at 50 megahertz, you want to have this operate very cleanly. When you turn these transistors off, and you're really doing it by turning one transistor off, and that kills all the other ones because of the way they're connected up, you want the other ones to shut off really promptly when this one does, and by the same token you want them all to turn on cleanly and very quickly when you turn this one on. So in order to assure that, this capacitor here helps this one be faster, and these capacitors here and here turns them on faster, so it speeds up the on to off transitions. And then something else that's done, this pull-up resistor here, which I was just saying, well, it's a pull-up, but I didn't know why it was there. Didn't seem like it would need a pull-up. And then this resistor is like, why is there a resistor between those two bases? Those are there to speed the transistors up. When you've got a transistor and it's in saturation, so it's fully on, fully off, it takes some time to come out of that. It slows the device down. So this transistor, for example, bleeds a little bit of base current into this. Not enough to really turn it on, but enough to keep it from completely turning off. Therefore, when you do want to have it turn on, it's already close to being able to do that. It doesn't have that sluggishness due to being in saturation before that. So that helps it turn on faster. And by the same token, having the base of the PNP and the base of the NPN tied together encourages both of them to be on just a tiny amount all the time. Still not enough to act like they're turned on to the rest of the circuit, but enough to make them come out of their hibernation, if you will, in a sprightlier fashion. So that's just a nuance of the circuit. So we've accomplished here the high-speed track and hold. Alright, so we've got this track and hold. I call it a sample and hold. Heathkit calls it a track and hold. And it's followed by this low-speed sample and hold circuit, which has an op-amp. Again, it's just reading the buffered output from the track and hold. Goes into this op-amp. It has a capacitor here with a really small value resistor. And then there's a dual gate MOSFET, which I know very little about, except that they're often used in the front ends of high-speed devices like, frequency counters and RF circuits and so on. In this instance, one of the gates is directly driven from the op-amp, and the other one, if you consider this to be a source follower, which it kind of has to be because the drain is tied right up to the plus 12 volt rail, then the source is the output, but it's also wrapped back around to the other gate. So I don't know if that acts as a kind of feedback. I'm not really sure. It's not my area of expertise by a long shot. Certainly the source is wrapped back around through this RC through to the negative input of the op-amp, so there is negative feedback here, and therefore the op-amp should adjust its output as required to make sure that both inputs match when it's operating normally. And this capacitor here is just going along for the ride in the middle of that feedback loop. However, this op-amp is a type with a separate bias signal that can be connected out from it. And there's a transistor here with its base tied to ground, and there's a TTL signal over here, TTL level. It's the sample and hold signal. where if it's in sample mode, it's a logic high. If it's in hold mode, it's a logic 0. So let's see what happens if you're in sample mode. So that's a logic high. This is a PNP. So now we've got a PNP with its emitter at a higher voltage than the base. So there's current flowing from the emitter to the base that turns the transistor on. The current, which would be controlled by, I think, the 5 volt logic here, TTL level again, through this 4.7K resistor, that's controlling the current. And that's going to go right through this now on transistor and provide some bias current to the inner workings of this op amp, allowing it to function normally. But if you want to do a hold on the signal, you take this to 0. That deprives this transistor of what it needs to operate, so it's essentially turned off. There is no bias current. The insides of this op amp can't function, and its output goes to high impedance state. Therefore, whatever is sitting on this capacitor is the only thing driving the gate of this dual gate MOSFET, and it doesn't know there's no feedback. It just knows it's, hey, I've got a voltage on the gate, and it acts as a source follower, and that voltage is buffered by this MOSFET and presented out here. So it's holding. It's like the sample and hold circuit in its hold mode. So very similar to what happened over here, but being used in a different way, accomplishing a similar goal, I think. I perused the Heathkit circuit description. They don't really make it very clear, I don't think it was clear at all, why it needs to have the high-speed track and hold followed by the low-speed sample and hold. Anyway, suffice it to say it's taking a snapshot of the signal, or it's letting the signal go right through it. That's essentially what's happening there. Other nuances, I'm sure, but I don't know what they are. Now that sample and hold is immediately followed by another op amp configured here. So it's got a 1K resistor going into the non-inverting input, essentially a short circuit back around to the minus input. So it's basically a buffer. There's a little RC hanging on here, but it's not a sample and hold circuit. It doesn't appear to be. And it's again driven by logic from the channel 1 select signal. And if that's on, then this transistor, just like this one here, it's the same exact setup, turns on, and you get a bias current dictated by the voltage here and the resistance, and this op amp is turned on. It's just functioning as a buffer, and the signal coming from here just goes right through it. But if you deselect channel 1 so that it's not working, then this transistor's off, there's no bias current, this thing doesn't do anything, and therefore its output is high impedance. And I suppose that this is like almost another sample and hold in this situation, that whatever's on this capacitor is going to sit there for a while. And then the output of that can be fed back around to this junction. Alright, after a bit more thought, there is a nuance to this, why this guy has to be here. We can't just use the output of this and go straight through, or not have this at all. It has to be there, because this is, after all, the channel 1 switch, and I described what that's doing just insofar as the channel 1 select signal, but there's more to it than that. There's also another signal summed into the plus input here, and that comes from this little cluster of transistors here, one FET and a couple of bipolar transistors. Now I drew it a little bit upside down. This should be, according to my schematic sensibility, should be drawn down here, because this is a higher potential and it's conducting down to a lower potential at ground. but essentially you've got a 5-volt supply that's called V-sup. I haven't been able to figure out where it comes from in the circuitry. I don't see a source defined for it anywhere, but it's some sort of a 5-volt signal. And this almost looks like a differential amplifier, but it's not. It's just two different transistors going from the V supply to this signal, and they each have their own trim pots, 100K trim pots. And there's a signal called the EQRT, which is the equivalent time real-time selector. It's really one signal, but there's an inverted and a normal version of it. So one of them is EQ, not RT. I should say this differently. If you're in RT mode, this will be 0 and this will be 1. If you're in EQ mode, this will be 0 and this will be 1. So one or the other of these is true at all times. Let's say you're in real-time mode, so this point is logically 1. That turns this transistor off, so it's not doing anything. This transistor gets turned, so it's not doing anything. This guy, on the other hand, is real-time mode. What I say, we're in real-time mode, right? So this is a 0, and that turns this PNP on, and therefore you have the V supply 5-volt going through the transistor, going through the trim pot, and then back around, and it sends some current up into this op amp. And that amount of current is adjustable by this. So this is the real-time mode 0. And at the same time, it's more than that. It looks like it's a this point doesn't just go up here. It's also got this trim pot and this FET going down to ground. And according to the potentiometer markings, that's the real-time mode gain. So we can adjust the gain on this a little bit by adjusting this trim pot. If you're in the EQ mode, however, now this pot acts like the 0 because this is the transistor that's turned on. And that would make sense because when you're in EQ mode, this is low, thereby that's going to turn this PNP on, and you've got current adjustable by this going up into this node. So by itself, it's the thing that turns the channel on and off, but it also allows calibration of this whole circuit essentially at this last stage, and also allows zeroing of it. So finally we get down here to this little amplifier. Heathkit just calls it the low frequency gain amplifier, which, what is that supposed to mean, right? One of the key points about it is channel 1 signal coming from up here goes to this node, and channel 2, remember channel 2 has got this entire circuit I just finished describing is duplicated for channel 2, and its output from its channel 2 switch comes to this point as well. The logic is only allowing one channel at a time to be on as far as this part of the circuit is concerned. So it's switching back and forth between them. Or if you're only trying to look at one channel, say only channel 1, you've got channel 2 turned off, then it won't even turn channel 2 on. But if you're looking at both channels 1 and 2, then they're going to be turned on and off alternately. Only one of them can be presented to this point at a time. This circuit here is a pretty classic precision rectifier or precision op-amp rectifier. So if the signal here is positive, let's ignore this resistor and this resistor for the moment. Pretend like they're not there. We just present the signal to the non-inverting input from whichever channel we've selected, comes into the non-inverting input. And if that's positive, then this diode is forward biased, and you drop the voltage across here. and then it has feedback going through this resistor, and being a non-inverting amplifier, the gain is determined by this resistor and this resistor. So you have some amount of gain, and the signal otherwise passes through and is dropped across this resistor. Now if you're in the opposite polarity, then this diode is reverse biased, and this diode is forward biased, and the signal still isn't getting through because this diode is reverse biased, therefore it can't get out to this point, but at least it gives the op-amp some continuous feedback so it doesn't just go off into la-la land. That's, in all these precision rectifier op-amp circuits, you want to have something so that the op-amp maintains some kind of feedback even when it's essentially switched off on the alternate polarity, and that's what this is doing. However, we've got this tweaked a little bit. In addition to the two resistors that are needed to establish gain in this configuration, there's also this resistor going up to the V sup, or plus 5 volt. I guess it's the non-logic 5 volt signal is probably what it is. It's 5 volts, but it's not coming off one of the logic power supplies. However it's getting from there, I don't know. I didn't find it in the circuit. But what that does is it acts like an offset. So it essentially, this has been calculated so that there's enough current coming this way to always make the op-amp push its output upwards. And the goal of that is not only is the signal coming through this rectified, so it can only be one polarity, but it's also offset. And the end result of that is the input signal over here is going to, probably look like this. I didn't draw it very symmetrically, but it's based around 0 volts. And the output circuit over here is going to have the same signal, albeit with some gain probably. And it's all going to be up above 0 volts. And that's necessary because the output of this goes to the analog to digital converter, and this particular analog to digital converter can only accept positive inputs. So we've taken all this other junk that we've conditioned the input signal, attenuation, amplification, sample and holds, switching, all that stuff, offsetting, gain adjustment, and then finally at the last stage we boost it up so it's all above ground and never goes below 0 volts. In case it does try to go to above 0 volts, this diode here would turn on and kind of clamp it to no higher than 5 volts. And that's necessary because that analog to digital converter that's downstream is designed to not have an input any higher than 5 volts. If you do, I don't know, you might damage it or something, I don't know. So this is apparently a safety diode. If there is any, if this does conduct, then this resistor would drop the extra voltage. So that's what's happening there. And keep in mind, this only occurs once. This is common to both channels. Now the signal comes around here, and I didn't have room on this page, so I just drew it down here in this corner. These are a couple of monostable multivibrators in one package. I think they're the same kind of IC that we had when I was looking at the logic circuit, and we had these two monostable multivibrators here and here for producing the 2.5 microsecond pulse and the 1 microsecond pulse. I believe it's the same kind of op-amp. And one of them takes the EQ SAM signal. Again, that's the equivalent mode sample command. It's and on its low transition, see if I can get this in the camera a little better, on its high to low transition it triggers this monostable and it produces an output pulse which is controlled by this resistor and this capacitor, the values of those. And it ends up being a 2.5 microsecond pulse. And then there's some logic in here. It's the sample and hold logic. I caught myself in the act of screwing up. This is in fact the same IC that I already touched on when I was looking at the logic part of the circuit. This is the same one, but it's more pertinent to the analog to digital converter than it is to the logic on whose page it was drawn. So this is the same one. It's not another IC doing the same type of thing. So you've got the EQ SAM signal that generates the 2.5 microsecond pulse, like I already mentioned. And then you've got that feeding into one of the inputs on this other monostable. It provides a positive going pulse. There's also the start A to D signal, which happens whenever the CPU accesses address 4000 or 4000 hexadecimal. When that specific address is accessed, the logic generates this start A to D signal. It goes low, and when it goes low, it's high to low transition, just like the high to low transition here. It acts as a trigger for this monostable. All these monostables here have a pair of inputs, and you can use one or both. In this case, only one of them is being used. In this case, both of them are being used, and they're essentially ORed together inside. So a high pulse from the 2.5 microsecond or the low going pulse from the start A to D signal, either one of those will trigger this, and it generates the 1 microsecond pulse. Now we've got the A to D converter. It's an ADC-0820, very common, very popular 8-bit ADC. Its VCC is generated off of the positive 12 volt supply and a 6.2 volt Zener diode. So you get 6.2 volts there. And then it's applied to the VCC of the ADC chip. The other end is ground. Everything's above ground on this, like I already mentioned. It's powered in the 0 to 5 volt range, and it's expecting a signal in the 0 to 5 volt range. And I mentioned before that the I/O addresses are decoded by the I/O decoder IC, and one of the outputs of that is the A to D. So the microprocessor says, I'm looking to get some data from an I/O device that's addressed as being the A to D converter. When the address lines up with that, that signal is generated, and it says to this IC that it's now time to read data. In other words, it's time to take the converted analog to digital signal and send it out. And it puts that on the 8-bit output, the data output of the IC. Now, I already mentioned how the signal coming from the this part of the circuit comes into the 0 to 5 volt input of the IC. Oh, I just found this up. I was looking for this before, and I forgot where it was. There actually is a 7805 on the circuit board that is just there for the purpose of generating the plus 5 volt V sub signal, and that is used to put the ADC into one of its possible modes, and it also provides the positive VREF or reference voltage that this chip needs. The minus VREF is just tied to ground, so I think that's another place where we're establishing the range of signals from the minimum to the maximum is 0 to 5 volts, essentially. That's what that's doing. And then when we get this 1 microsecond pulse coming from here, then it actually says, and it's coming from the inverted output here, so it's a negative pulse. And we have the output here, and that goes low, and this is also read, so it's boom, puts the data out on the data bus, and the CPU can read it. That's how it takes one sample. And then the thing I'm not really clear on, and I don't think the Heathkit instructions explained it adequately, you know, we're supposed to be looking at a waveform where you need to take samples a lot during the course of the waveform or you don't get the wave shape. There is no hardware that I found on the circuit study which indicates there's anything in the hardware that's really generating that. It has to be generated in logic. So apparently there's something in the microprocessor code that strobes everything through here so that it takes a whole bunch of samples. And if we're in real-time mode, it would have to be doing that because otherwise you wouldn't get a waveform. In the equivalent time mode, something a little more elaborate's going on, and I can just describe what the circuit is doing, but since I don't really know all the nuances of what's going on in the software, I don't think I can describe it much better than that, but that is my best crack at taking an overview of this analog portion of the circuit. Okay, the rest of the circuit is the so-called trigger circuit, and it has a number of sections, and I've redrawn them here to make it a little easier to follow. On the analog circuit we looked at a little while ago, I mentioned that there's this emitter follower that we tap off, and it provides the channel 1 trigger signal. It's a secondary output in parallel with the one that the actual signal that gets passed on to the sample and hold circuits comes from, but it has a similar signal on it. The two trigger signals, one from channel 1, one from channel 2, are brought together in this relay, and I'd mentioned in my internal overview of the circuit that there seemed to be an extra relay in between the two channels. Everything else was symmetrical, and there was this one extra relay sitting in there, and right next to it was a shielded cable leaving the circuit board, jumping over about half the board and going back into the circuit board. That's this. This is that extra relay, and this is that piece of shielded cable. So it's basically selecting which of the two channels we're going to use as the source of the trigger. And that is something that the user selects through the front panel or through the connected computer. You know, which channel are you going to use as the basis of your trigger. So that's sent over here, and we have a differential amplifier, as classic as it could be. Couple of transistors, similar configurations, and their emitters are joined together, and there is a transistor to some sort of a negative power rail, so that's there. And then there is also a adjustable trigger level trim pot here, which the goal is to maintain some sort of a voltage on the base of this transistor so that it acts like a constant current source, or more specifically in this case, a constant current sink, the better to make this differential amplifier work. Normally you would just have a voltage divider or something on this that would provide that reference, usually with a Zener diode in it or something for best stability. In this case it's a little more elaborate. Well, here's an area that the Heathkit description doesn't cover at all, so I just figured it out for myself best as I can. There's another, or a digital to analog converter here. It's an 8-bit one, and it gets its inputs off of 8 discrete signals that are generated from one of the latches on the I/O data bus that it was already covered. Now they're identified here as A, B, C, D, E, F, G, H. I do not know offhand if they are used in conjunction like in a binary pattern or if it's a 1 of 8 thing. I suppose it's used in a binary pattern. Anyway, it's set up so that it has a 5 volt VCC and a VEE that's minus 12, and it also has a ground. That's because this is both a digital and an analog device. It has a current output, not a voltage output, but a current output. And then that goes into this op amp, which is configured to convert the current signal into a voltage signal, and that's what it's doing. So these two things together make up the trigger level signal. Now that goes through a voltage divider, which knocks it down quite a bit, so it becomes, I imagine this voltage can swing pretty widely between 0 and 5 volts, for example. And then you're going to knock it way down, so it's 1,130 ohms over 47.5 ohms, so it knocks it way down. It becomes a very small signal. And that goes around and it gets hooked up to the other input of the differential amplifier. This whole line here is plus 12 volts. It just sort of snakes around the way I drew it. And it's providing the Vref plus right off the 12 volts, essentially. And the minus Vref, or Vref minus, is essentially going to a minus 6.2 volt power rail generated off the minus 12 volt with another 6.2 Zener diode. So that's giving you your minus ref here. So this is actually below ground, and I suppose therefore that if this works the way I think it works, the output signal is bipolar. It can go above ground, it can go below ground. We also have derived off this minus 6.2 volt voltage divider. It splits it exactly in half, equal value resistors. So you'd have a minus 3.1 volts there. And that's presented as an offset to this op amp. So whatever signal you're generating here, based on the reference inputs, gets boosted by 3.1 volts, made more positive by that amount. And again, that is fed back as one input to the differential amplifier here. Now, it's a little bit more than a simple differential amplifier. This is, of course, subject at pretty high speeds. It can go up to 50 megahertz. And you start running into problems with bipolar transistors, at least a lot of them, when you start running them fast. And you'll see this also in some of the higher frequency counters, that when they do transistor amplifiers, there's internal capacitance inside these which make them start acting crappy at higher frequencies. And one way around that is to put them in a so-called cascode transistor or cascode amplifier configuration, where the in this case the collector, one of the outputs of the differential amplifier, goes through this transistor and the other output goes through this transistor. Both of their bases are tied to a fixed voltage. So you have your plus 12 volts here, goes through this diode and this resistor to this point, then another resistor to minus 12 volts. So this is roughly halfway between plus 12 volts and minus 12 volts, according to the voltage divider, and then it's filtered for stability right in the middle there. So that's essentially 0 volts here. However, because of this diode up here, it's skewed just a little bit. The diodes here actually to compensate for thermal drift in this transistor and this transistor and this transistor. Thermal drift in any of these will skew the way this works. So the designers figured out by putting this diode here, its thermal drift will be, I think, in the opposite direction from that of the transistors, so it sort of compensates for it a little bit. Anyway, you're holding the bases of these two transistors at essentially 0 volts. It's not ground, it's a virtual ground. And when you hold a transistor's base at ground, or virtual ground in this instance, it can no longer amplify voltages, but it can amplify currents. And used in conjunction with voltage amplification transistors here, that's what forms the cascode pair between this transistor and this one, between this transistor and this one, and it overcomes the capacitive effects in here, so it works better at high frequencies, is the upshot. And now we get into a piece of circuitry which is very familiar to people who've studied the inputs to frequency counters, you know, where you're dealing with higher frequencies. It's also something often seen in transmission line circuits, and it's using one of this family of Motorola ICs, in this case the MC10116. It's an ECL part, so emitter coupled logic, and it's much faster than a regular logic, so it's used in these higher frequency circuits. It's also done differentially, or in a balanced mode, like a balanced line, so that's why you have two outputs on all of them, and they're complementary to each other. When one goes high, the other one's going low, and vice versa. And they have to be terminated like you would a transmission line. So we have these two signals coming out of the differential amplifier, and they're more or less complementary because it's a differential amplifier. And they've been cascoded, and those two signals are applied to the inverting and the non-inverting input of the first amplifier. And there's, again, these three amplifiers in one IC. So you get a little bit of amplification out of this. And its outputs are terminated to VCC in this case. You might say, well, why isn't that tied to ground? Well, ECL logic wants to be operating with its so-called VCC at ground, and the thing you might normally consider to be the negative rail or ground in a normal circuit is actually a positive voltage. So that's why they're terminated to VCC, whereas their VCC pin is actually tied to ground. The whole thing is kind of upside down. That's just an ECL thing. But we're only using the output of this first stage, just the non-inverting output. It goes into the second stage, and this IC generates an internal bias voltage or something like that. I don't really understand it. But it's coming out of this. I'm just going to call it the VREF. It's like a reference voltage that it outputs. And I had it shown here on one of them, but it's really common to all three. Just a convenient place to draw it. And that, along with this resistor and this resistor, from the inverting output to the inverting input, that causes this second stage to be acting as a hysteresis amplifier. So it's taking the analog signal that's coming here, which could have any wave shape, could be a sine wave, triangle wave, whatever, and it's snapping it to whatever voltage reference is applied here. It's snapping it above that or snapping below that, so it squares up the signal and gives it a very very fast rise and fall times. There's also a little bit of amplification in there as well. So that's what that second stage is doing, and again, its outputs are terminated to the VCC power rail. And then finally we have an additional gain. It just has inherent gain. It doesn't require any external resistors to get that. I don't think it's a lot of gain, but it's another gain stage. And the output again is terminated to VCC. Then we go into another ECL part. So this is an ECL part. It's the MC10102. So it's in the same family as the 10116 that we just looked at. So again, it's ECL. I can't say that often enough. So its VCC power supply line is tied to ground, and its VEE is going to a minus voltage reference. These two NOR gates in the IC are tied together on their outputs, so it's a wired OR kind of circuit. And one of the outputs from this stage goes to this one, and one of them goes to this one. And then there's a signal here. This is from the slope signal of the digital logic. It's one of the outputs from the I/O bus latches. It's determining whether the scope is going to be triggering on a rising level or on a falling level. Well, this is a TTL signal over here. We need to convert it to ECL voltage levels, and that's done with these three resistors. So it's a TTL to ECL voltage level translator, and that's applied to this input here and also to this input, the other input of which is just tied to a minus voltage reference, so it's just acting like an inverter here. So you're essentially taking the slope signal and you're putting its non-inverted version into this OR gate, and you're inverting it and applying it to that gate. The upshot is, if the slope signal back here is a logic 1, then the output at pin 2 is locked low. If the slope is at a logic 0, then pin 2 is the inverted version of the pin 4 input. Otherwise, this one is the inverted one. So it's essentially combining those two signals, and it does it according to whether the slope is positive or minus. And then you get this single output here. There's also this fourth NOR gate, and this one actually has a differential output as opposed to the other three, which just have a single inverting output. This one isn't being used, so its output is just tied to VCC through a resistor. Good practice. The output of that comes over here, and you've got a pair of flip-flops. This upper I should say these two flip-flops are in a third ECL package, in this case an MC10131. It's a dual D-type flip-flop, so two D-type flip-flops in one IC. This one arms this one, so we have another signal coming from the microprocessor. This actually comes from the BUSAK signal directly. It's a pin on the Z80 microprocessor. TTL levels, it's the bus acknowledge, I think is what it stands for, and it's active low. It's inverted by this inverter so that it's active high. The TTL level is converted to ECL level by these resistors. It's just the same as what we did here for the slope signal. And this ECL level goes to this input to this flip-flop. These two OR gates are part of the flip-flop IC. This is supposed to be conditioning the clock inputs to the two flip-flops, but the way it's being used here, it's just a pass-through. So when you get that bus ACK signal, it goes in here and acts as the clock to this flip-flop. Normally that would cause whatever's on the D input to be transferred to the outputs, but the D inputs are tied to logic, well, to ground, but again that's in an ECL environment, but let's not worry about that too much. So this guy here, once it receives that signal, it arms this flip-flop, which is the trigger flip-flop. And if it's triggered, then when it gets the signal from up here, then it like locks that in. And again, this is ECL, and we need to now get it from ECL voltage levels back to TTL voltage levels so the rest of the logic circuit can use it. Because this is an ECL device with complementary outputs, Q and Q naught, we have to terminate those to, in this case, the minus VC with termination resistors. And then the uninverted one goes to the base of this transistor, the inverted one goes to the emitter. And this is a pretty common technique for converting ECL, complementary ECL outputs to a single-ended TTL output. So this transistor is either on or off, and when it's on, it's shorting this pin to a lower potential. If it's off, then this resistor pulls it up. So this is a logic 0 or 1, and it basically means we've got a trigger signal coming from here. The logic has said we're waiting for a trigger signal, so it arms this one by locking in that pulse on this one. This guy's armed. When it does see a trigger signal, it acknowledges that and it locks it in. The signal gets converted to TTL, and that is essentially saying we've got our trigger and we've taken action. There's also a CLR trig. I wrote it kind of funny here, CL space R trig, but it's CLR trig. It's clear the trigger. This is another signal coming from the I/O decoder, of which there are many signals, but this particular one does this. Again, it's a TTL signal. It has to be converted to ECL, so another set of 3 resistors. The bottom of it's tied to minus VC again, and that's also what's powering the flip-flop IC. But this output, this ECL level output, again from the clear trigger level shifter, and that comes over here and goes to the reset of this guy. So it resets this stage, and when it does that, the Q naught output turns on, which is what happens when you reset this flip-flop, and that guy turning on wraps around to the set of this one and sets it on, which, when you've got these D-type flip-flops, if you're not clocking in some data on the D, then you can force them to have their output set on or off by the set and reset inputs. This one can only be set because reset isn't tied to anything. This one can only be reset because the set isn't tied to anything. But again, the whole thing is, you say, I should point out that this bus ACK signal, I looked it up, it's normally high, but it goes to 0 when the CPU stops running in preparation for a trigger event. So it's doing that, and I had to look this up in the Heathkit description because I didn't know why it was doing it. And it just has a brief note saying it's doing that so that all the bus activity and everything on the CPU does not cause so much digital noise that it could throw off the triggering and gives you false triggering. So it's like the CPU is saying, I'm going to be doing a trigger now. I want to have the quietest logical environment for that, so I'm actually going to stop running, or if not stopping running, at least stopping its bus activity. It's saying, hey, the bus is turned off. We're not going to be toggling all that crap. And that's what gets this guy set, and then it arms this guy. Once it does get triggered, then that signal is read back in, and the CPU is allowed to resume operation again. It only should take a split second. But I think that's what's going on there, as near as I can figure it out. So now we have the trigger signal coming out of here, and we go into this transistor here. And this is a part that I'm a little confused about. I haven't thought about it quite hard enough. But there's a ramp circuit on here. I think this has to do with the CPU figuring out where we are in the repeated signal that we're trying to measure. Since it's doing the sample and hold, I already mentioned, it's sampling that at a particular time, taking a sample, And I said earlier, well, how does it do that for the rest of the signal? I think this is how it does it. There are 3 signals coming from the I/O data bus, and it's called ramp A, B, and C. There's actually 4 of them. Just 3 of them are here. The 4th one is used elsewhere. And there's a couple of 1 of 8 ICs here. There's 2 of them actually. And these 3 signals, ramp A, B, and C, they have, I think these are open collector outputs, and they have these pull-up resistors to get them up to logic high, and they feed the A, B, and C inputs of this IC and the A, B, and C inputs of this IC. Same kind of IC. There's these 8 resistors here, and they're in progressive values. So 1,438 ohms, 2,678, 7,150, 14.3, 28. They're basically, each one's double what the other one was. And it can only be one of those. They cannot be used in binary combinations because they're being driven from these 1 of 8 ICs. So only one of those can be active. And then there's this other one that's doing the same thing, and it's tied to the same resistors. What's that all about? I scratched my head on that for a little bit. But it has to do with what follows. This is actually a ramp circuit here. And so it's an op-amp. And it has a stable voltage reference applied to its non-inverting input. So plus 12 volts, 6.2 volt Zener. So you develop 6.2 volts, but it has this voltage divider across it. And that's the low frequency horizontal calibration. So you're picking off a particular point there and applying it as the positive or non-inverting input to this op-amp. But then the rest of this is a little hard to figure out, so I redrew it. This is essentially what we have here. You've got the op-amp with its reference voltage already described. The output of it drives this transistor, which has a 5 volt Zener, and then it goes back into a feedback arrangement. So redrawing that again, here's the Zener, and there's this 1 meg resistor that's up here, and that's here. And then we have this resistor, and that resistor is one of these. And it's connected to 2 places. It's from plus 12 volts, and it's connected to here and to here. These are essentially switches, and that's exactly why there's 2 of these. This one here is acting as one of these switches. This one's acting as the other switch. But because there's actually 8 resistors, there need to be 8 switches here and 8 switches here. Where they come together is a different value resistor depending on which 2 switches are closed. So that's what's going on there. It makes a little more sense when you look at it this way. If you apply a voltage to an op-amp like this, and it has feedback, and in this case a current is being applied here, this turns it into a constant current source, and it's feeding a particular constant current this way through the PNP transistor and out. So you get a different constant current depending on which resistor is applied here. So that's what this whole circuit is doing. It's a programmable constant current source that can be one of 8 constant currents. And then over here we have 3 capacitors. 1, 2, 3. These 2 are just tied straight to ground. This one is tied to ground through a transistor. And I mentioned before that there is a 4th ramp signal besides ramp A, B, and C. Here's the 4th one, ramp D. This also comes from the I/O bus latch, just like the other ones did. And that is used to turn on this transistor. Then if this transistor is on, it puts this capacitor in parallel with these other 2 capacitors that are always there. So how is the ramp generated? The ramp is going to have a waveform that looks like this. It'll charge up in a linear slope, then drop down, and then charge up, and then drop down, and charge up and drop down. That's your ramp signal. This is the transistor that's shorting that out. So this is the circuit that's charging up the capacitor. And when you charge a capacitor with a constant current source, instead of having a curve that goes up on a curve that goes up on a curve, right? It'll instead be linear, so it goes up on an even slope. So that's what's happening there. Programmable constant current source going into charging capacitors. These are smaller value capacitors, and they're used when you need a faster ramp. But sometimes, especially at lower frequencies, you want a slower ramp, and that's when this ramp D is turned on. It brings in this transistor, which brings in this larger capacitor. Compared to the values of these, this is a much bigger capacitor, so when this is engaged, it's like these ones aren't even there. So collectively, they're charging at least two of them, sometimes three of them. And that, along with the programmable constant current, is resulting in a variety of ramps that are charging at different rates. And periodically, the reset ramp signal, again coming from the trigger circuit over here, is resetting it, and it starts charging up again. So I'm thinking, why is it doing that? And what I believe is happening is you're taking a sample, and then this is kind of equivalent to the sweep, I think, or at least a time interval. And you need to figure out where on that ramp you are, and when you get to it, you detect that you've reached that point on the ramp. And I think that it's not exactly the same, but you can kind of think of it as being the sweep of the signal. Or you can think of it as being the time delay before you have to do another, before you need to trigger again, something along those lines. I haven't completely got my head around it. I feel like I'm 95% there, but I'm too lazy to dig into it more, so I'm just going to leave it at that. So we need to read this voltage that's ramping up, and it's done with this little circuit here. It's very much like all these other ones we've done several times in here. You've got a source follower, an FET set up as a source follower. So a very high impedance input monitoring this. The output is taken here, but for this to operate properly, you have to have a constant current going through it. This second FET, which is in the same package as this one, so they track each other thermally. This, with its gate tied to its source, it acts like a constant current drain or a constant current sink. And that, again, helps this guy to operate. You take your output from it, and this is your buffered ramp signal. This IC here is a comparator. It has a lot of extra stuff on it, strobes and things like that, which we're not using. What is it comparing this ramp against? Well, it's comparing it against not an 8-bit, but a 10-bit, or an analog signal that's the result of a 10-bit digital to analog converter. The input to this digital analog converter comes again from more bits that are latched on the I/O data bus, so it's under processor control. And you end up with 10 bits of resolution. You have an analog output. This is really just a bunch of resistors and FET switches that are combining the resistors in a binary pattern according to whatever bits are on or off here. There is hardly any active electronics in here other than the little FET switches. So the output comes here. It's 512 voltage levels to take care of the EQ time samples. The output is plugged back into here and goes on the other side of those resistors, so it acts like a feedback loop. So it's more accurate. The output is divided down a little bit, somewhere on the order of a third of the voltage is taken away and 2/3 are used, and that's just to get the voltage range in line with what the ramp is doing. You're doing the comparison, so at some point along that ramp you're going to reach the level that's set here by the microprocessor, and when it reaches that, the comparator is going to flip the other way. And then every time you do a reset, now the voltage on the ramp will be lower than the signal coming from the digital to analog converter, so the comparator will flip the other way again. So you get not a square wave, but a pulse wave, and this particular comparator has complementary outputs, so you have the complement as well. The output is running at logic levels because its output switching circuit is tied to VCC, not to plus 12 volts. So you have above 0 volts, you have a pulse wave, and you also have above 0 volts a pulse wave, but they're complementary. When this one's high, the other one's low. So those feed into the sample command and to the microprocessor's interrupt, directly into the microprocessor's interrupt pin. So that's obvious. The microprocessor is sitting here waiting for the ramp to cross the programmed level over here, and when it happens it generates an interrupt. Stops it from whatever else it's doing so it can service that, and again, that's all part of the overall sample and hold and trigger scheme, which is just too complicated to go in here. The complement of it is fed into the EQ SAM signal that I already discussed, where it's commanding another sample to be taken in the EQ mode, or the equivalent mode. So there's all that stuff going on. Now I mentioned before there's the bus active signal, which is important when you're going to be setting up a trigger to be triggered by the trigger event up there. And here's how, this is the counterpart to that. There's the clear trigger signal again. We have the clear trigger up here, and there's the complement of it down here, the inverted clear trigger. And that's going into this gate here, which is looking at the interrupt signal, and it's combining those logically, and it's generating the bus required signal. So this is what's telling the Z80, okay, we've set up now to take a sample or to wait to be triggered. You better cease all bus activity until further notice. And as soon as the microprocessor acknowledges that and has stopped its bus activity, then that's what allows this trigger circuit to here to be set or to be armed. And as soon as that's done, then that all feeds back around and allows the processor to resume normal operation. It's, again, too complicated to discuss in the context of this video. So the CPU is waiting. It's stopped while awaiting the trigger. If no trigger occurs for some reason, so it's been armed, the bus activity is stopped, but what if the trigger event never happens? Maybe the voltage level is wrong for the trigger level that's been programmed, so it never gets triggered. Or you've just disconnected the input to the scope, or the triggering is set to a channel you're not using, or something like that, so the trigger never happens. So this circuit here is an edge-triggered kind of thing. So you get the clear trigger signal, and it passes it through, but then it slowly recovers due to the capacitor charging through this resistor to the point where it cancels itself after some period of time. So that's why this capacitor is there and this resistor is there. And this diode's just there. When this guy discharges, it helps it recover faster. I think that's what's going on with that. So, that's my big picture overview of the whole way the triggering works on this scope. Alright, so the part I've covered so far is applicable to both the ID-4850 and the IC-4802. Again, that's the version without the ability to operate with an analog scope connected and without any front panel controls. The 4850 having both those extra features. Everything I've talked about up to this point is applicable to both models. Now we're getting into the territory that's only applicable to the ID-4850, because this all deals with the front panel and the extra outputs to go to an analog scope. So we already know from the previous schematic, the one on the microprocessor and the logic circuitry, there's that connector that goes off board, and it has some unregulated DC voltages, plus 9 volts, plus 17 volts, minus 17 volts. So it's filtered but not regulated. There's ground, there's I/O requests, there's the M1. We have the 8 I/O data bus lines. That's ID0 through ID7. That again is the special version of the microprocessor's data bus that's used just for I/O interfacing. And then we have select address lines. We have address lines 0, 1, 2, 3, and then 8, 9, and 10. And a couple more grounds. So everything on the two front panel boards uses those signals. So first off, we take the 3 raw unregulated voltages and run the plus and minus 17 through a 78L12, that's the low power version of the 7812 12 volt regulator, and the 79L12, the low power version of the 7912 negative regulator, negative 12 volt regulator. And then the plus 9 volts goes through a regular 7805, that's the normal version that handles more power. So we have the 3 voltages established just for use on the two front panel boards. We have to condition the lines coming from the address bus. Address 0, 1, 2, and 3 are used in yet another decoder, just like the other decoders we had on the other board that take 3 inputs and turn it into one of 8 outputs. So that is used here, just like the similar ones on the main logic. This handles all the extra signals on the front panel boards, so it's like an extension of the several of them we had on the main logic circuit. That gives us this one here, which is primarily the voltage indications, the LEDs for channel 1. This one does the same thing for channel 2. This one handles both channels, their AC, ground, and DC coupling LEDs, as well as the plus and minus slope signals. Again, these are all for driving LEDs. And this IC has, and this is a little bit multiplexed. It's done in 2 banks, but they share lines because of the multiplexing. So there's LEDs for 1, 2, 5, 10, 20, then going up to 50, that shares a line with 1, and 100 shares a line with 2, 200 shares a line with 5, 500 shares a line with 10. So 5, 6, 7, 8, 9 different numerical values, which are unitless in this regard. And if we're going to do the LEDs 1 through 20, then this line also turns on. if we're going to do the LEDs 50 through 500, then this line turns on, and that's in that multiplex scheme. Now we don't know what the units are on those yet, so the next 4 lines on this next decoder chip give us the signals for nanoseconds, microseconds, milliseconds, and seconds, and those provide the units for these guys up here. So those go out and directly drive their LEDs. And then finally we have plus level, 0 level, and minus level coming out of that same IC. And then there's one more similar IC that has the LEDs for auto, normal, single. That's the triggering. There's ready, that means trigger ready. Channel 1 triggering, channel 2 triggering, save. And this last one is not an LED. It's trigger, and that's the signal that's actually providing the trigger signal to go to an analog scope. It does not go to an LED. Let's see, I think I covered all that. All of these ICs have enough ability to not source current to LEDs, but to sink current from LEDs. Like so many TTL chips, they have more sink capability on their outputs than they do source. So if you're going to drive an LED off of them, it's better to sink the current into the IC than source it out to the LED. All those make their way through all these connectors here, of which there are 4, and that just gets all those signals over to the front of the 2 front panel boards. The only other thing that's on this board is the vertical output for driving the vertical input of a connected analog oscilloscope. There's another 8-bit latch here, and it takes those 8 data bus lines. Now it identifies them here as D0 through D7, but in reality they're the ID0 through ID7, so they're on the I/O data bus. And those go directly into this chip, which latches them in, and it's clocked by a signal from the decoder up here, the same one that selects all these other chips. And it is actually the same exact model of IC as all these others, so it works the same way. Then its output goes up here and goes into the 8 inputs on an 8-bit digital to analog converter IC. I think we've seen this IC elsewhere in the circuit. It's the DAC0808, and it works about the same way. We establish a voltage. Well, actually, it's the one coming from the V reference, minus V reference, which is sourced from the main board, and that's brought over here, and it's brought in as the minus reference voltage on the DAC, and it's also divided, I think in half. Yeah, divided in half as the positive input of this op-amp. So like the other instance of this, the output of this particular DAC is current, not voltage. So we take it and go into the op-amp configured in such a way as to provide us with a voltage output converted from the current output of the DAC. And because it's biased up like this, or biased down as the case may be, because this is a minus voltage, this signal here will be all above ground, just like it was previously. The DAC can only work, or the ADC, these are all designed to work in the positive voltage realm. So this is a positive output voltage that would result from this, but now we're hitting it with a half of the power supply rail negative voltage as its plus input, and that shifts everything down, so we end up with a signal that is half above ground and half below ground. It's a bipolar signal, as you would expect. And there's a voltage divider coming out of that with a output calibration trim pot, so you can get exactly the right voltage from what's intended. And then it goes out a pad on the circuit board and goes to the vertical output BNC connector. Going back to the trigger output on this other IC that I touched on before, this is a TTL level signal, and it just operates this transistor here, which provides a little more drive current and protection for the IC. If you hook up something stupid over here, you blow up the transistor maybe and not the IC. So this just provides a logic signal, 0 to 5 volt logic signal, comes out of a pad on the circuit board and goes to the trigger output BNC connector on the front panel. So there is one more aspect to this rear of the two front panel circuit boards, and that's these three buffers up here. These are driven by the upper three address bits. Remember I said we were bringing in address bits 0 through 3 and 8 through 10. Already described what happens with the 0 through 3. By the way, the 3 is used as a chip enable for this latch, whereas the other three, A0 through A2, are actually used to provide the 3 bits of binary control for the 8 outputs. We've got those 3 other bits now, A8 through A10, and those come directly up here. Each one drives a different buffer in this one IC rather. These are buffers with tri-state outputs, so if you do nothing with these additional inputs, the G inputs, then they operate normally, but if you provide a logic 1 on those, it essentially disconnects the output, so it tri-states them or high impedances them, if you will, so that from the rest of the circuit it appears that these lines here, here, and here are not connected to anything. They're just floating. And that G signal for all of those comes from a pin on the connector, which comes from the read command to the bidirectional data transceiver. It's just a way of turning this whole circuit on its head, if you will, because everything else on here is about outputting something. Outputting signals to turn LEDs on, outputting signals to generate a vertical output analog signal, outputting a signal to operate the trigger output. But there are push buttons on the front panel, and those are input devices, so how do we handle those? And that's what these are about. The switches on the front panel are arranged in a matrix, and just to sketch that out really quickly, if I had a 4x4 matrix like that, I might drive these. Well, let's pretend, let me get rid of this one because we've only got 3 signals here, so those would be driving into these 3 rows, and then there's a bunch of columns. I only drew 4 here, and at each of these intersections is a push button switch that shorts its respective row and column together at that point if you push the button. So one at a time, the microprocessor turns on one of those address bits, so that turns on one of these 3 after being buffered, and then if a switch is pushed, it shorts that signal to one of the columns, and those are connected back to the data bus, so that it can the processor can read that and figure out from knowing which row is turned on and which data pin is now energized. It can figure out which button was pushed. That's the essence of the switch matrix. This is just a small version of it I sketched. So for this to work properly, we need to take all of these lines and tie them high. So they have resistors going up to VCC. And then these lines are read off on the data bus. So if a switch is not pushed, then this, if nothing is shorting it to one of these lines, then the resistors pull it up, and then pushing a button, if the button is connecting it to a row that is pulled low by logic from the address, then that will pull the respective column low, and that can be read on the data bus. So that's what's happening there. And that's why down here there's this resistor network. There's 8 of them in there, and it's typical of the Heathkit things. They would show it wherever it's convenient to show it. So they show it here as if it's associated with this latch for the analog or digital to analog converter. And while electrically it's correct to have it here, it would have made more sense to show these pull-up resistors on the next drawing where all the switches are at, kind of like I did here. But that's just a little misleading where they located it. It makes you think it's got nothing to do with the switches unless you trace all the signals back and see that it is there for that reason. So how do those data lines get out to the front panel circuit board? Well, there's otherwise unused pins on these 4 connectors, and they're just scattered around there. So there are some signals that are coming here, like D0 comes over to a pin here, D1, D2, or D4. So 0, 1, and 4 are brought to otherwise unused pins here. D2, D3, and D5 are brought to pins here. And D2 and D3 and D6 and D7 and D4 again are also brought to this connector. I think that's just for convenience in how the traces on the front circuit board are set up, that it brings only the data bus bits that are pertinent to the other wires on those connectors. So there is some duplication, but that's how those signals get there. Alright, we're almost done with this slog through the schematics. This is the schematic for the front panel board, and there's really no intelligence on it. There's no analog circuitry, there's not really any active digital circuitry. All there is on here is a bunch of LEDs, a few resistors, and some switches. So let's take a look at the first connector coming from the rearmost front panel board. And this is the one that handles all the LEDs for the voltage sensitivity and coupling LEDs for channel 1. So we have the 5 millivolt LED, 10 millivolt, 20 millivolt, 50 millivolt, 100 millivolt, 200 millivolts, 500 millivolts, 1 volt, 2 volt, and 5 volt LEDs. And these are in 2 different groups. I mentioned before they're kind of multiplexed. So these 1, 2, 3, 4, 5 LEDs have their anodes on one wire, whereas the other 1, 2, 3, 4, 5 have their anodes on another wire. And those come back to these 2 pins on the connector. And back on the other drawing, there's resistors here coming from the latch ICs. So you can only have one of these LEDs on at a time, and they're in the 2 groups. So the worst you can ever have is one LED on active on one of these lines, so it only needs a single current limiting resistor. But because there are 2 lines, it needs 2 current limiting resistors. They really could have done it with 1 resistor, except then that would have used up 10 I/O pins. Doing it this way, it uses up fewer. It uses 7 I/O pins. 2 for the columns over here, and 5 for the rows, if you will, going to the LEDs. And then directly driven without multiplexing are these 3 LEDs for DC coupling, ground, and AC coupling. So those are not multiplexed. They have a single resistor here from VCC to provide current limiting to whichever one of those is on. And if none of those are on, that means the channel is turned off. The same exact circuit is here for channel 2, done exactly the same way, but there are some differences in how the other pins on the connector are used. On this one, there were no signals that were not part of the channel 1 LEDs, but on this one, in addition to the channel 2 LEDs, there are the data 0, data 1, data 4, and address 8 lines coming from there. Now going over to the next group, the next connector, this one also has a multiplexing scheme like these do. You have the LEDs for 1, 2, 5, 10, 20, 50, 100, 200, and 500 broken into two groups with their commons coming from two current limiting resistors on the other circuit board, and then the cathodes driven, so each line handles two cathodes, one up here and one down here, and the next line does this one and so on, although there's 5 here and only 4 here. And then we have direct drive without multiplexing for the units of measurement for the horizontal, so you have seconds, milliseconds, microseconds, and nanoseconds, and that whole group of 4 has a single current limiting resistor from VCC. But there's also this additional LED here, that's the save LED, that has its own dedicated current limiting resistor, and it goes back to one of the pins on the I/O bus latch ICs. Finally, we have this last connector, and it's very similar to this. It has 3 LEDs. That's for auto, normal, and single. Those are the triggering modes, and each are driven independently, and they share a single current limiting resistor. Then there's also the ready LED, and that has its own dedicated line and current limiting resistor. Then we have the LEDs relating to triggering, and it's in a group of 2 for minus slope and positive slope, another group of 2 for channel 1 trigger and channel 2 trigger, and then a group of 3 for minus level, 0 level, and plus level. Either of these can be on, either of these can be on, either of these 3 can be on, so each of those groups has its own current limiting resistor. Otherwise they're directly driven, it's not multiplexed. So that takes care of all of those LEDs. And then finally, I already mentioned the switch matrix, and here are the buffered address A8, A9, and A10 that we already looked at as being buffered on the other drawing. And here are the 3 rows, and here are the 1, 2, 3, 4, 5, 6, 7, 8 columns, each one associated with a I/O data bit, D0, 1, 2, 3, 4, 5, 6, 7. So it's really that simple. There doesn't seem to be any particular grouping on here that I've sussed out so far. Here's the channel 1 position up, channel 1 position down, channel 2 position up, channel 2 position down, trigger level up, trigger level down. This one has the trigger slope button, the trigger mode button, reset, trigger source, and save. This one has channel 1 sensitivity up, sensitivity, or channel 2 sensitivity down, channel 1 sensitivity up. I think there's a typo on there. One of those is channel 2. Let's see, this is channel 2 sensitivity down. This one also says sensitivity down, so that's a mistake. One of those has got to be up. So up, down, up, down. I think they put the channel numbers incorrectly on these. Then we have channel 1 coupling button, channel 2 coupling button, time base increase, time base decrease. And that's all that's on that front panel.